When you think about darkness, you probably imagine something empty, a quiet room after the lights are out. But in the universe, darkness can be a source. It can shine not by giving off light itself, but by shaping it, bending it, and fueling it in ways that defy intuition. What we call empty space is filled with invisible forces so powerful they can trap light forever, yet somehow create the brightest objects we've ever found. For centuries, scientists thought they understood how the cosmos worked. Stars burned, planets orbited, and light traveled in straight lines. Then we discovered places where all those rules break down, where time slows to a crawl and space itself bends like fabric. These discoveries didn't just change astronomy, they challenged everything we thought we knew about reality itself. In this video, we'll explore one of the most extreme examples of cosmic power and learn how something invisible can outshine entire galaxies. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The numbers that describe ton 618 stretch beyond what our minds can comfortably hold. When scientists speak of 66 billion solar masses, they're describing something that exists at the very edge of possibility. Our own sun, already incomprehensibly massive compared to Earth, becomes a grain of sand next to this cosmic giant. The event horizon, the invisible boundary where escape becomes impossible, would swallow our entire solar system with room to spare. This black hole sits more than 10 billion light-years away, so distant that its light began traveling toward us when the universe was barely 3 billion years old. Back then, galaxies were still young and chaotic, nothing like the organized spirals we see today. Our solar system didn't even exist yet, wouldn't exist for another 5 billion years. Every moment of Earth's entire history, from the first stirrings of life to the rise of consciousness, has unfolded while this ancient light crossed the void between galaxies. What makes ton 618 truly puzzling is how it got so large so quickly. Black holes typically grow slowly, feeding on nearby matter over billions of years, but the universe simply hadn't been around long enough for normal processes to create something this massive. It's like finding a 1,000-year-old tree in a forest that's only been growing for a century. The mathematics don't quite add up, and that's what makes it fascinating. Perhaps in the early universe, entire gas clouds collapsed directly into black holes without ever becoming stars first. Maybe black holes merge together more frequently than we imagine, like cosmic droplets combining into larger pools of gravity. Or maybe there are feeding mechanisms we haven't discovered yet, ways for these objects to consume matter faster than our current models predict. The light we receive from ton 618 has been stretched by the expanding universe, shifted toward the red end of the spectrum in a process astronomers call redshift. This stretching tells us not just how far away the object is, but also how much the universe has grown since that light began its journey. Each photon carries within it a timestamp from the cosmic past, a message written in wavelengths of color. Around the black hole spins an accretion disk, a whirlpool of gas and dust spiraling inward at tremendous speeds. As this material falls toward the event horizon, friction heats it to millions of degrees, causing it to glow brighter than entire galaxies. The irony is remarkable. Something that traps light forever creates some of the brightest displays in the universe through the violence of its feeding. This brightness was first noticed decades ago by astronomers conducting radio surveys of the sky. They catalogued it simply as another data point, not knowing they had discovered one of the most extreme objects ever found. Only later did improved instruments reveal its true nature. A quasar powered by a supermassive black hole devouring matter on an almost unimaginable scale. If we could somehow move ton 618 much closer to us, say 50 million light-years away, it would shine nearly as bright as our full moon. Of course, at that distance, its gravitational effects would likely tear apart nearby star systems. But the thought experiment helps illustrate just how energetic this distant beacon really is. The physics near such an object become increasingly strange. Space itself warps like a stretched fabric around the black hole's immense gravity. Time flows differently there. slowing down relative to regions of weaker gravitational pull. These aren't just theoretical curiosities, they're measurable effects that challenge our everyday understanding of reality. What strikes many people as almost mystical is how something so distant can teach us about the fundamental nature of space and time. The spectrum of light from TON 618 reveals the chemical composition of matter that existed when the universe was young. We can read the signatures of hydrogen and helium in wavelengths that have been traveling for over 10 billion years, carrying information across cosmic distances. Black holes represent perhaps the ultimate victory of gravity over all other forces. When enough matter concentrates in a small enough region, not even the nuclear forces that power stars can resist the inward pull. What remains is a point of infinite density surrounded by an event horizon, a boundary beyond which the normal rules of cause and effect break down. The study of objects like TON 618 pushes astronomy to its limits. We're forced to piece together evidence from faint signals to infer the properties of something we can never directly observe. It's detective work on a cosmic scale, using mathematics and physics to reconstruct events that happened billions of years ago in regions of space we'll never visit. Perhaps most humbling is the realization that TON 618 was already ancient. When our galaxy was young, it existed as a mature, fully grown monster, while the Milky Way was still assembling itself from smaller collections of stars. In cosmic terms, we're newcomers trying to understand the relics left behind by a much older, more violent epoch of universal history. The light reaching us now from TON 618 began its journey when the universe looked completely different. Galaxies were closer together, star formation was more chaotic, and the cosmic web of matter was still organizing itself into the large-scale structures we observe today. By studying this ancient light, we're essentially performing archaeology on the universe itself, uncovering clues about conditions that existed long before Earth formed. Light moves faster than anything else in our universe, but even at that incredible speed, it takes time to cross the vast emptiness between stars. When we look up at the night sky, we're not seeing things as they are now, we're seeing them as they were. Some of that light began its journey before our planet even existed. There's something almost magical about how telescopes work. They collect incredibly faint whispers of light, photons that have traveled unimaginable distances without ever stopping, never resting, never slowing down. These tiny particles of energy strike the mirror of a telescope and get converted into electrical signals, then stored on computer chips. Human eyes look at the data and somehow find meaning in it, patterns that tell us about objects so far away they're barely more than mathematical concepts. The universe operates on scales that can make your mind feel stretched thin. When astronomers measure distances in billions of light years, they're talking about light that has been traveling for billions of years without interruption. No pause, no obstacle, just constant motion at the ultimate cosmic speed limit. Each photon carries information from a time so ancient that nothing familiar existed yet. Black holes present us with one of nature's most beautiful contradictions. We call them black because nothing can escape their gravity. Not even light, but the ones we actually discover are usually among the brightest objects we can observe. They don't shine because of what they are, but because of what they do to everything around them. Matter falling into a black hole doesn't just disappear quietly, it puts on quite a show. As material spirals inward, it forms what scientists call an accretion disk. Imagine a whirlpool, but instead of water, it's made of superheated gas and plasma. The friction and gravitational forces heat this material to temperatures that would tear atoms apart. It glows with desperate energy, emitting X-rays and ultraviolet light that can be detected across the universe. The physics behind all this follows the same basic principles that govern a drain in your bathtub. The difference is only in size and consequence. Where your bathtub creates a small vortex, a supermassive black hole creates a cosmic maelstrom that can outshine entire galaxies. Some black holes take this process to almost unimaginable extremes. The magnetic fields around them can twist into narrow jets of plasma that shoot out from the poles, spearing through space for thousands of light years. These jets are among the most powerful structures in existence, bright enough to be seen across the observable universe. There's a quiet irony in studying these objects. We're essentially watching fossils of energy, ancient records of chaos that helped shape the galaxies we see today. Every distant bright point in space tells a story about how the universe built itself, one collision and one meal at a time. Our own galaxy, the Milky Way, appears calm and spiral-shaped now, but it owes its current form to similar violent forces that once raged in its youth. At the center sits our own supermassive black hole, something called Sagittarius A. Today it's relatively quiet, almost sleepy by cosmic standards, but perhaps it was once as voracious and bright as the most distant objects we can detect, shining across the cosmos before settling into middle age. When you think about it this way, those incredibly distant, incredibly bright black holes might not be just curiosities. They could be glimpses of our own galaxy's violent past, reminders of how creative and destructive the universe once was. The process of astronomical observation itself carries a kind of quiet reverence. Here we are, small intelligences on a tiny planet, somehow able to notice echoes of immense things. The universe is mostly empty, expanding, and dim. The energy that reaches us from the most distant objects is unimaginably weak, yet with the right instruments, we can read that faint light and reconstruct entire histories. We can determine how fast matter was moving billions of years ago, how hot it was, how much energy it released, even what chemical elements were present, all from light so faint you'd never see it with your naked eyes. That's the real miracle of modern astronomy, finding profound meaning in whispers. The universe keeps most of its secrets hidden. We've mapped only a small fraction of what's out there, and there are certainly larger, more massive black holes waiting to be discovered. Some might be shrouded by dust and distance. Others might be so far away that their light simply hasn't reached us yet. It's humbling to remember that the night sky above you, peaceful as it might appear, conceals billions of galaxies. Each one likely harbors a supermassive black hole at its center, quietly shaping the fate of everything around it. Most of these cosmic monsters will remain forever unknown to us, their stories playing out in regions of space we'll never see. Distance has a strange way of making even the most violent objects seem almost gentle. A supermassive black hole, something that could tear apart entire solar systems, becomes an object of study rather than fear when it's billions of light years away. We can admire it, analyze it, let its existence remind us how vast and varied the universe truly is. The light from these distant objects is still traveling outward, still expanding through space, still telling stories to anyone capable of listening. Billions of years from now, that same ancient light might reach other worlds, other species with their own telescopes and questions. Perhaps they'll look back through time and see what we're seeing now, bright points in the darkness, proof that something immense once burned at the edge of creation. There's something profound about sharing this moment of awareness with light that's older than oceans, older than every living thing that has ever looked up at the night sky. In the midst of all that cosmic distance and indifference, human consciousness acts like a mirror, catching fragments of the universe and turning them into understanding. The act of noticing, wondering, caring to know, this is what connects us to the stars. These distant objects may be beyond any possible reach, but the curiosity they inspire is immediate, alive in minds that imagine them. Even the most massive black hole, something so dense it bends the very fabric of space and time, becomes part of our inner landscape when we contemplate it. In the quiet of contemplation, you can let these images settle. Somewhere out there, ancient light carries messages across eons, patient and steady. The message is beautifully simple, that even in the deepest darkness, something endures, something shines, and we, small and temporary as we are, can still listen. When we close our eyes at night, darkness feels like emptiness, like a gentle absence of everything bright around us. But out in the cosmos, darkness behaves in ways that would surprise you. It doesn't just swallow light, it actually creates some of the most brilliant displays the universe has ever produced. Think about this for a moment. The darkest objects in existence, black holes, are surrounded by the brightest light imaginable. It's one of nature's most beautiful contradictions. The matter that spirals toward these cosmic giants doesn't just disappear quietly. Instead, it puts on a spectacular light show, heating up to millions of degrees as gravity compresses it, beyond anything we can recreate on Earth. TON 618 represents this paradox at its most extreme. This black hole, sitting billions of light years away from us, outshines entire galaxies. The energy it produces, moment by moment, equals about 100 trillion of our suns. Imagine trying to count that high, then imagine each number representing the brightness of the star that gives us life. What makes this even more remarkable is how efficient this process really is. Most energy production in the universe wastes enormous amounts of material. Stars burn hydrogen for billions of years, but they only convert a tiny fraction of that fuel into light. Chemical reactions that power our bodies, they're even less efficient. But when matter falls toward a black hole, up to 40% of its mass transforms directly into pure energy. This means TON 18 operates like the universe's most powerful engine. Every month, it consumes material equivalent to several stars, not gently, but through violent storms of magnetic fields and superheated plasma. Each atom that gets pulled inward contributes to the glow we can detect across billions of light years of empty space. The light itself tells us stories we couldn't learn any other way. By measuring how bright this object appears, astronomers calculate exactly how much matter it devours. The flickering patterns in that brightness reveal the structure of the spinning disk around it. Matter orbits so close to the black hole that it completes full circles in just hours, moving at speeds that approach light itself. If you could somehow survive a journey to see TON 618 up close, you wouldn't see a dark hole at all. The black hole itself remains invisible, hidden behind its own brilliant accretion disk. What you'd witness instead is a blazing white and blue inferno, pulsing and shimmering as space and time bend the light around it. The actual boundary where light can no longer escape would be impossible to see, buried in the center of all that glare. This boundary, the event horizon, stretches about 390 billion kilometers across. Light itself would need over a day to travel from one edge to the other. Within that region, the normal rules of physics start breaking down. Time stretches and warps, moments near the edge, lasting forever from an outside perspective. The scale here defies easy comparison. Our own galaxy contains a black hole at its center, but TON weighs 16,000 times more. That's not just a bigger number. It represents a fundamentally different class of object. The gravitational influence extends so far that entire solar systems could orbit within what we consider the black hole's immediate neighborhood. What strikes many people as almost philosophical is how destruction and creation intertwine at these cosmic scales. Black holes don't just consume everything around them, they actually help regulate galaxy formation. They heat up surrounding gas clouds, controlling how quickly new stars can form. Without this balance, galaxies might collapse too rapidly or grow without any organized structure. The light we detect from TON 618 left its source about 10 billion years ago. Back then, the universe was much younger, and this black hole was probably even more active than it appears today. The radiation we observe has been traveling through space for most of cosmic history, growing fainter and redder as the universe expanded around it. By the time this ancient light reaches our telescopes, it's just a whisper of its original intensity. What once blazed with the fury of a cosmic lighthouse now appears as faint radio waves and X-ray emissions. Yet even this diminished signal carries enough information for us to understand the violent processes that created it. Most of the energy TON 618 produces doesn't shine in visible light at all. The temperatures involved push most radiation into ultraviolet and X-ray wavelengths. If you could somehow see this object with human eyes, it might appear dimmer than you'd expect, even though it's producing more energy than anything else we've ever discovered. This raises interesting questions about perception and reality. The most energetic processes in the universe often remain invisible to us without special instruments and keepings. And prouder, IRP keeper. Your own cold, the science. We live in a narrow slice of the electromagnetic spectrum, seeing only a tiny fraction of what's actually happening around us. TON 618 reminds us that the universe operates on scales and in ways that our everyday experience never prepared us to understand. The matter falling into this black hole doesn't follow gentle, predictable paths. Magnetic fields twist and reconnect, creating jets of particles that shoot outward at nearly light speed. These jets can extend for thousands of light years, carrying energy far beyond the galaxy that hosts the black hole. It's a system of incredible complexity, where destruction at the center enables creation across vast distances. Scientists classify objects like TON 618 as quasars, short for quasi-stellar radio sources. When astronomers first discovered these objects in the mid-20th century, they appeared as simple points of light, like ordinary stars. But their spectra revealed they were neither ordinary nor nearby. The light showed redshift values that placed them at enormous distances, making them far more luminous than entire galaxies. This discovery fundamentally changed our understanding of the universe. It showed that black holes weren't just exotic theoretical objects, but active participants in cosmic evolution. They shaped the formation of galaxies, influenced star creation across vast regions, and create some of the most spectacular phenomena we can observe. The study of objects like TON 619 also reveals something profound about the nature of time and distance in astronomy. When we observe distant objects, we're literally looking into the past. The universe TON 618 inhabited 10 billion years ago was denser, more chaotic, with galaxies colliding and merging more frequently. The intense activity we observe reflects those ancient, more violent conditions. Today, that same region of space probably looks very different. The black hole may have consumed most of the nearby matter, settling into a quieter state. The brilliant accretion disk might have faded, leaving behind a dark, nearly invisible giant. We're seeing the ghost of cosmic violence, preserved in light that's been traveling toward us since before our solar system formed. When we think about black holes spinning, we're not just talking about simple rotation, like a ball turning in space. What happens is much stranger than that. The black hole actually grabs onto the fabric of space itself, dragging it along like thick honey being stirred by a spoon. This creates something called frame dragging, where even completely empty space near the black hole starts moving, whether it wants to or not. Picture this. Anything that gets close enough doesn't have a choice about orbiting. It's not gravity pulling in the usual sense. It's the actual geometry of space that's been twisted into spirals. The faster these cosmic giants spin, the more energy gets squeezed out of all that swirling matter around them. Those massive jets, shooting from the poles, they're like cosmic fire hoses powered by this spinning motion. The brightness we detect from these distant objects hints at just how rapidly they're spinning. They channel magnetic fields into beams that stretch across distances we can barely imagine. These aren't just pretty light shows either. They're real structures cutting through gas and dust, carrying energy and particles way beyond the edges of entire galaxies. Some of these jets are so powerful they actually influence how neighboring galaxies form. Think about that for a moment. One spinning black hole can affect the birth of stars in completely separate cosmic neighborhoods, millions of light years away. Each jet becomes like a power line connecting the black hole's rotation to the wider universe around it. The strange comfort in all this violence is that it happened so long ago, so far away. We're watching ancient history play out in real time, a cosmic movie that finished its run before Earth even existed. That light reaching us now, it's like a memory preserved in photons, traveling across space for billions of years just to tickle our instruments. By the time we see it, the source itself might have changed completely. Maybe it's gone quiet, consumed everything nearby, now just sitting there as a dark core in a dead galaxy. Or maybe it's still shining brilliantly, its current light racing toward worlds that haven't even formed yet. There's something beautifully contradictory about how darkness can shine. The glow around a black hole isn't fighting against physics, it's following the rules perfectly. Gravity pulls matter inward, which forces energy outward. The darker the center gets, the brighter the surrounding halo becomes. It's like a cosmic trade-off, a balance that keeps the whole system running. This same principle shows up everywhere in the universe. Nuclear fusion works this way. Supernovas follow the same pattern. Even life itself depends on pressure creating heat, destruction leading to light. Black holes just take this rule and scale it up to galactic proportions. What makes these objects so mesmerizing is how they warp everything we think we understand. Distance becomes meaningless. Time slows down. Light that should travel in straight lines curves back on itself. From far away, matter falling into a black hole appears to freeze at the edge, never quite crossing over. But from the matter's perspective, the journey is quick, a brief plunge into nothingness completed in moments. Both viewpoints are correct, which tells us something profound about reality. The universe doesn't care about our everyday experience of how things should work. It operates according to stranger, deeper rules that become visible only under the most extreme conditions. When astronomers describe these distant powerhouses as cosmic lighthouses, they're capturing something important, but incomplete. A lighthouse guides ships safely to harbor, warns them of danger. These cosmic beacons do something similar, but unintentionally. They guide our understanding, showing us what happens when the laws of physics get pushed to their limits. Every photon that reaches us traces the path of matter under conditions we could never recreate on Earth. They let us test our theories about gravity, magnetism, thermodynamics, all from the comfort of observatories built on solid ground. In a way, each observation tightens the connection between our mathematical equations and the actual behavior of the universe. It's easy to forget, sitting in a quiet room or walking on a calm night, that the cosmos contains such incredible violence. Yet somehow this realization brings peace rather than fear. These distant giants exist in perfect equilibrium, consuming and radiating, enduring across cosmic time. Their light travels through expanding space, gradually softening into faint signals that we can barely detect. That faintness is part of their story. A reminder that even the greatest powers in the universe eventually fade into background whispers. But those whispers are enough for us to hear, to wonder about, to learn from. When scientists study these objects, they use every type of light available. Radio telescopes trace those massive jets stretching across space. Optical instruments measure the specific signatures of hydrogen gas. X-ray observatories peek into the innermost regions where temperatures reach tens of millions of degrees. By combining all these different signals, researchers build a complete picture not of what these objects look like to human eyes, but of how they behave, how they evolve over time. Even after decades of careful observation, fundamental questions remain unanswered. How did these giants grow so large in so little cosmic time? Were they born big, or did they feed with unusual efficiency? Did they form from primordial clouds of gas untouched by earlier stars, or through chaotic mergers in young, violent galaxies? Each possible answer leads to new computer simulations, new telescope designs, new nights spent analyzing data that might contain the clue that solves the puzzle. These distant objects become both subjects of study and challenges to overcome. Open questions written in light that's traveled for billions of years. Beyond all the data and mathematics, there's something deeply human in how these discoveries make us feel. A mixture of awe and calm, a quiet recognition that the universe is far older and larger than anything we can properly measure. Yet, somehow still knowable, we small beings, made from the same atoms that once glowed in those distant disks, can look outward and understand at least a fraction of what we see. The brightness we detect isn't just about photons hitting our instruments, it's about the knowledge those photons carry. Light that reaches not just our eyes, but our sense of where we fit in the grand scheme of things. Right now, somewhere far beyond our horizon, energy released from these cosmic powerhouses is still moving outward, still expanding, still illuminating regions of space we'll never see. Every second, those waves spread a little farther, touching galaxies beyond our reach, gradually fading, but never completely disappearing. This is what makes the idea of shining darkness so compelling. It reminds us that the universe is never entirely still, never completely silent. Even the deepest black contains a pulse of light waiting to be discovered, waiting to tell us something new about the strange and beautiful cosmos we inhabit. Light carries stories across impossible distances, and when we catch photons from distant quasars, we're essentially reading messages written billions of years ago. The photons reaching us from the most distant objects began their journey when the universe was fundamentally different, younger, more chaotic. These ancient travelers have witnessed the entire span of cosmic evolution, moving through space while galaxies formed, stars ignited, and entire civilizations could have risen and fallen along their path. What's fascinating about astronomical observation is that we never see anything as it exists right now. We're always looking backward through time. The moon appears as it was just over a second ago. The nearer stars show us their state from years past, and the most distant galaxies reveal themselves as they existed when the cosmos was still learning how to organize matter into the structures we recognize today. This creates an interesting philosophical puzzle. The night sky presents us with a beautiful illusion, a tapestry woven from different moments in cosmic history. Some stars we observe have already died, their light still traveling toward us, like echoes of their former brilliance. Others are being born right now, but we won't see that birth for years or centuries to come. Time becomes layered, scattered across the darkness in points of light. Space itself has been expanding since the very beginning, stretching the wavelengths of light as it travels. This expansion leaves fingerprints on every photon, shifting their colors toward the red end of the spectrum. By measuring these shifts, astronomers can calculate not just how far light has traveled, but when it began its journey. It's like having a cosmic timestamp embedded in each ray of starlight. The persistence of light across such vast distances is remarkable when you consider everything it encounters. Gravitational fields bend it, dust clouds scatter it, magnetic fields twist it, yet enough photons survive their billion-year journeys to carry detailed information about their origins. Each surviving photon becomes a messenger, carrying data about temperature, composition, motion, and energy from objects so distant they might not even exist anymore. When astronomers break this ancient light into its component wavelengths using spectrographs, they're essentially performing cosmic archaeology. Different elements leave unique signatures, absorption, and emission lines that reveal the chemical composition of distant objects. Hydrogen creates one pattern, helium another, carbon and oxygen each leave their own distinct marks. It's like reading hieroglyphs written in the language of physics. The most distant quasars show us the universe during its adolescence, when black holes were actively feeding and galaxies were smaller, denser, more prone to collisions. Star formation happened at furious rates back then. These luminous beacons help us understand how cosmic structure evolved, how the web of matter that fills space gradually organized itself into the patterns we observe today. Some of these ancient black holes challenge our understanding of how quickly such massive objects could form. According to standard models, there simply wasn't enough time in the early universe for certain supermassive black holes to grow through normal feeding processes. Either they were born unusually large from the direct collapse of massive gas clouds, or they found ways to consume matter far more efficiently than we previously thought possible. This raises deeper questions about the nature of time and growth in cosmic contexts. Perhaps our earthbound intuitions about how quickly things can develop don't apply to environments where gravity warps space-time itself. The extreme conditions around these early black holes operated under physics that we're still learning to understand. Every photon that reaches our telescopes completes a journey that began eons before humans existed to catch it. These particles have no mass, no charge, no internal clock marking the passage of time, yet they carry perfect records of their birthplace across billions of years. They're immune to the erosion that affects everything else in the universe. Light serves as the fundamental connection between us and the cosmos. Every piece of knowledge we have about space comes from catching and analyzing electromagnetic radiation in its various forms. Visible light, radio waves, infrared, ultraviolet, X-rays, all of these are photons carrying information from distant sources. We've built instruments to catch them, amplify them, sort them by wavelength, and translate their patterns into understanding. In a sense, astronomy is the art of listening to these ancient conversations. The universe speaks through light, and the most distant objects speak in the oldest dialects. When we point our telescopes toward the edge of the observable universe, we're not just looking through space, we're looking through the history of existence itself. The light from the most distant quasars has been traveling for so long that it carries information about conditions that no longer exist anywhere in the universe. The dense, star-forming regions of the early cosmos gave way to the more spread out, evolved galaxies we see in our cosmic neighborhood. Those ancient environments were laboratories where the elements heavier than hydrogen and helium were first forged and scattered. This creates an interesting temporal landscape. The universe around us exists at different ages simultaneously, depending on how far we look. Nearby galaxies show us cosmic middle age, distant ones reveal cosmic youth, and the most remote objects visible to us capture cosmic infancy. We live surrounded by this chronological diversity, this museum of cosmic evolution, displayed across the night sky. The philosophical implications ripple outward from this realization. If we can only observe the past, never the present, then our entire understanding of the universe is built on historical evidence. We're cosmic historians, piecing together the story of existence from ancient light. The universe as it exists right now, in this moment, remains fundamentally unknowable to us. When we catch light from distant objects in space, we're really catching whispers from the past. These photons have been traveling for billions of years, carrying stories about what the universe looked like when it was young and wild. The ancient light tells us that complexity existed much earlier than we might expect, that massive black holes were already growing to enormous sizes, that the fundamental forces were already at work, shaping everything we see today. This continuity between past and present runs deeper than we often realize. Every wave of light connects different moments in cosmic history, building our current reality layer by layer. The atoms in your body, the carbon and oxygen that keep you alive, were forged in the cores of stars that began shining billions of years ago. This isn't poetry. It's physics, a literal connection between your existence and ancient stellar furnaces. If you could somehow travel back 10 billion years and stand near one of these distant galaxies, the sky would be unrecognizable. Our Milky Way wouldn't exist yet. The nearby galaxies would be smaller, younger, packed more closely together. Space itself would buzz with radiation from newly formed stars, a cosmic nursery where the building blocks of everything familiar were just taking shape. Light travels at about 9.5 trillion kilometers per year. When we multiply that by 10 billion, the numbers become so vast they lose all meaning to our everyday experience. Yet human curiosity, paired with clever technology, can detect signals so faint they're just a few photons per second. We can turn that whisper into knowledge about entire galaxies, about black holes millions of times more massive than our sun. Every astronomical observation depends on a kind of cosmic accident, a brief alignment between our position in space and the path of something ancient. The fact that we can look at a tiny point of light and recognize it as a black hole from the early universe speaks to something remarkable about human perception and ingenuity. As this ancient light traveled toward us, the expansion of space itself changed it. What began as intense ultraviolet radiation has been stretched into deep red or infrared wavelengths. This stretching carries information about how fast the universe has been expanding, about the mysterious force we call dark energy that seems to be accelerating that expansion. The oldest light we can detect, the cosmic microwave background, comes from about 380,000 years after the Big Bang, when atoms first formed and space became transparent. The light from distant quasars comes from billions of years later, when structure had emerged, when matter had clumped together into the first galaxies. By comparing these different signals, astronomers trace how the universe assembled itself, how gravity gathered matter into increasingly complex patterns. Every new observation fits into this broader timeline, a history written not in words, but in electromagnetic radiation. When you really think about it, this ancient light is older than memory, older than the molecules that make life possible. And yet here it is, reaching us now, bouncing off mirrors and detectors, built by human hands in the 21st century. The connection between such different scales, cosmic and personal, makes astronomy uniquely powerful. It reminds us that our curiosity, small as it might seem, participates in the same process that creates galaxies and stars. In a sense, it's the universe becoming aware of itself through our observations. On a dark night, far from city lights, the faint glow of stars represents history arriving at your eyes. Some of those photons began their journey when humans first learned to control fire. Others started traveling when dinosaurs walked the Earth, or when our planet was still molten rock. The light from the most distant objects, invisible to our eyes, but captured by telescopes, reminds us that space and time are fundamentally connected. Here's something that might bend your mind a bit. From the perspective of a photon, no time passes during its journey. The moment it leaves its source and the moment it hits a detector are, for the photon itself, the same instant. Physics tells us that at the speed of light, time stops. So when we say we're seeing these objects as they were billions of years ago, what we really mean is that we're receiving light that never aged. Our universe changed around it. Space expanded, galaxies moved apart, stars lived and died, but the light simply continued, unbothered. This creates a strange and beautiful contrast between what is and what is perceived. To us, there are 10 billion years of cosmic evolution separating the emission and detection of this light. To the light itself, there was no journey at all. It's a silent, perfect record of endurance, crossing a universe that was itself growing and changing. As this ancient light continues to reach our telescopes, it invites us to keep looking deeper. Beyond the brightest, distant quasars are countless fainter ones, each sending its own message from the early cosmos. Together, they weave a map of how the universe looked when it was young, showing where matter first gathered, where gravity began its patient work of construction, where the seeds of all current structure took hold. Each new discovery adds another point to this vast pattern, another piece of evidence that we live in a universe still filled with echoes from its youth. The light may be ancient, but it's not finished teaching us. Every new telescope, every improvement in our methods of analysis refines our understanding of what happened during those first cosmic epochs. As we continue to collect these photons, we keep assembling a story that stretches beyond time as we normally experience it. It's a story still unfolding in the faint glow that crosses the endless dark, connecting the deepest past with our present moment of discovery. The universe operates on principles so simple you could explain them to a child. Gravity pulls things together, matter falls toward other matter, energy spreads outward as light. These basic rules, repeated across billions of years, create everything we see. Stars form, galaxies spin, planets orbit in predictable patterns. But sometimes, those same gentle laws produce something so extreme that our understanding breaks down entirely. Deep in space, roughly 10 billion light-years from Earth, sits an object that challenges everything we think we know about cosmic limits. Scientists call it TON 618, a name as plain as a grocery list item. The designation comes from an old survey catalogue, nothing fancy or poetic about it. Yet behind those simple characters hides something that defies imagination, a black hole containing 66 billion times the mass of our Sun. When astronomers first calculated those numbers, they went back to check their work multiple times. The figures seemed impossible, even in a universe already full of impossibilities. They were looking at something that existed on a scale beyond ordinary measurement. We already had a term for enormous black holes, calling them supermassive. But TON 618 needed something beyond that category entirely. Think about our Sun for a moment. That burning ball of gas contains nearly all the mass in our solar system, about 99.8% of everything nearby. Earth, Jupiter, Saturn, all the planets combined, barely register as a rounding error compared to the Sun's bulk. You could fit more than 1 million Earths inside the Sun's volume. Its gravity reaches across billions of kilometers, keeping every planet, locked in its dance. Now, try multiplying that mass by 66 billion. The result is ton 618, an object whose gravitational influence could swallow entire solar systems like ours without even noticing. Multiple star systems could orbit inside its reach, nested like Russian dolls, each one pulled inexorably inward towards something they could never escape. If you somehow moved ton 618 to the center of our solar system, replacing our familiar sun, its event horizon would stretch past Neptune's orbit. The event horizon marks the point where gravity becomes absolute, where even light cannot climb back out. Our entire solar system would fit comfortably inside that invisible boundary. The black hole's diameter spans nearly 400 billion kilometers. Light itself, traveling at the fastest possible speed, would need more than a full day to cross from one side to the other. For comparison, sunlight takes just over 8 minutes to reach Earth. Those numbers represent more than size. They represent a fundamental shift in how reality works. Inside that boundary, the normal rules change completely. Nothing can escape, not matter, not energy, not information. The escape velocity, the speed needed to break free from ton 618's pull, exceeds the speed of light. Since nothing moves faster than light, nothing gets out. The event horizon isn't a surface you could stand on or touch. It's more like a mathematical boundary, a place where the geometry of space and time bends beyond recognition. Cross that line and direction loses meaning. Up and down, forward and backward, all point toward the same destination, the center. At the very heart of ton 618 lies something called a singularity, where density becomes infinite and space curves so sharply that physics breaks down. Whether that infinity actually exists, or whether it just shows the limits of our equations, nobody knows for certain. What we do know is that near the singularity, space and time weave together so tightly that past and future become indistinguishable. For an object as massive as TON 618, that central mystery scales up proportionally. It's not just bigger, it's more consequential. The unknown region at its core affects a volume of space larger than most solar systems. Gravity doesn't just bend light near TON 618, it fundamentally rewrites how time passes. The stronger the gravitational field, the slower time moves relative to areas farther away. If you could somehow hover safely near TON 618's event horizon, time would crawl compared to the rest of the universe. Seconds for you might equal years for distant observers. The black hole creates an unbridgeable gap between its neighborhood and everywhere else, not just in space but in time itself. Light trying to escape that gravitational prison loses energy in the struggle. Photons stretch out, their frequency drops, their color shifts toward the red end of the spectrum. To someone watching from far away, the innermost regions of ton 618's surrounding disk appear to move in slow motion, their glow dimmed by gravity's grip. This isn't science fiction. It's been confirmed by studying closer black holes that we can actually photograph. The material around ton 618 forms what astronomers call an accretion disk, a swirling mass of gas and dust spiraling inward. That disk glows incredibly bright as friction and compression heat the infalling matter to millions of degrees. The faster the material spins and the stronger the gravity, the hotter and brighter everything becomes. By analyzing the light from that disk, scientists can estimate both how massive the black hole is and how fast it rotates. Ton 618 appears to be feeding near something called the Eddington limit, a delicate balance between gravitational pull inward and radiation pressure pushing outward. When a black hole accretes matter that quickly, the energy released becomes so intense that the light itself starts pushing back against new material, trying to fall in. Ton 618 operates right at that maximum efficiency point, like a cosmic engine running at full throttle. Even at that theoretical limit, its appetite remains staggering. Ton 618 consumes thousands of Earth masses worth of material every single year. But it doesn't feed smoothly or quietly. The accretion process is chaotic, turbulent. Magnetic fields twist through the disk, creating hotspots where energy surges and fades unpredictably. Matter spirals inward unevenly, causing flickers in brightness that astronomers can detect even across billions of light years. Those tiny fluctuations in light reveal the black hole's feeding patterns, like watching a giant's pulse through the glow of its meal. For perspective, compare TON 618 to the black hole at the center of our own galaxy. Sagittarius A weighs about 4 million times more than the Sun. That's enormous by any human standard, but it's practically microscopic next to TON 618. Our local galactic monster would fit inside HON 618's event horizon tens of thousands of times over. Sagittarius A sits quiet these days, barely eating anything, producing just a faint glow. TON 618, meanwhile, blazes with the energy of active feeding, announcing its presence across the entire observable universe. They're both black holes, but they exist in completely different categories of power and influence. Theoretically, black holes have no maximum size limit. They can keep growing as long as material keeps falling in. Galaxies crash into each other, merge together, feed their central black holes through billions of years of cosmic time. Each collision can double or triple a black hole's mass. Given enough time and enough food, the mathematics allow for objects even larger than TON 618. But TON 618's existence creates a puzzle for cosmologists. The early universe wasn't supposed to produce such giants so quickly. Current models of galaxy formation struggle to explain how any black hole could reach billions of solar masses in less than a billion years after the Big Bang. For TOT 618 to exist, where we see it, 10 billion light-years away, it must have grown to full size incredibly fast. That rapid growth suggests either our theories about early star formation are incomplete, or something unusual happened during the universe's youth. Maybe there was a period of super-efficient accretion, or perhaps massive seed black holes formed directly from collapsing gas clouds, instead of from dying stars. The existence of TON 618 forces scientists to reconsider what was possible in the cosmic past. Einstein's famous equation, E=mc², shows us that even tiny amounts of matter contain enormous energy. TON 618 converts vast quantities of infalling material into pure radiation, releasing energy equivalent to millions of supernova explosions every single second. That radiation pressure becomes so intense, it actually sculpts the surrounding galaxy, blowing away gas clouds and shutting down star formation in nearby regions. This feedback loop explains why galaxies and their central black holes seem to grow together in lockstep. The black hole doesn't just sit passively at the galactic center, it actively regulates its environment. It prevents runaway star formation, maintains a kind of cosmic balance, keeps things from spiraling completely out of control. TON 618 operates as more than just an isolated monster lurking in deep space. It functions as a structural component of the universe itself. Its gravity influences billions of stars within its host galaxy. The energy from its feeding affects regions millions of light-years away. The black hole doesn't just live in its galaxy, it defines that galaxy's fundamental character. To visualize these proportions, imagine the Milky Way as a sprawling city of stars, with our modest black hole Sagittarius A as a central plaza. TON 618, by comparison, would be like an entire continent compressed into a single intersection. The gravitational landscape it creates dwarfs everything in its vicinity. Every star, every gas cloud, every piece of matter moves according to its influence. If we could visit TON 618's galaxy, we'd see a brilliant compact center surrounded by halos of stars and dust, all slowly circling a point that could never be safely approached. The black hole's jets of high-energy particles would stretch across intergalactic distances, carving channels through space itself. There's something almost architectural about how TON 618 organizes its surroundings. Despite having no consciousness, no intention, no goal beyond following physical laws, it creates structures on galactic scales. Its gravity becomes a sculptor, its radiation a paintbrush, its magnetic fields, the invisible framework holding everything in dynamic tension. The clinical name, TON 618, feels oddly appropriate when you think about it. The universe doesn't need flowery titles or dramatic descriptions. The grandeur is built into the object itself. Sometimes scientific understatement enhances the sense of wonder rather than diminishing it. The idea that we can compress something containing 66 billion solar masses into 3 letters and a number speaks to both our intellectual hubris and our genuine capability. We detect TON 618 not through direct observation, but through careful inference. The black hole itself remains invisible, defined by absence rather than presence. But the material around it glows with incredible intensity, creating what we call a quasar. That light, born from destruction at the edge of nothingness, travels for billions of years to reach our telescopes. By the time those photons arrive at Earth, they carry information about conditions near 618 from when the universe was much younger. We're seeing ancient light from a cosmic furnace that was already fully grown when our solar system hadn't even formed yet. The light itself becomes a time machine, a messenger from an era when galaxies were closer together and black holes grew more aggressively. The paradox of studying black holes is that these invisible objects often produce the brightest phenomena in the universe. TON 618 generates more light than entire galaxies, all from matter's final moments before disappearing forever. It's a cosmic lighthouse built from gravitational collapse, a beacon that shouts its presence across billions of light years while remaining fundamentally unknowable. Perhaps that's what makes TON 618 so compelling beyond its record-breaking statistics. It represents the boundary between what we can measure and what we can truly comprehend. Our instruments can detect it, our mathematics can describe it, our computers can simulate it, but our intuition, evolved to navigate Earth-sized problems, simply cannot grasp what it means. We persist in trying to understand anyway, because that effort itself defines something essential about human curiosity. We're creatures who look up at the night sky and wonder what's out there, even when the answers challenge our capacity to imagine. TON 618 stands as a testament to both the universe's creativity and our own stubborn desire to measurable. In the end, this massive black hole reminds us that reality operates on scales far beyond human experience, following rules that seem simple until you push them to their logical extremes. Gravity, given enough time and material, can create structures that dwarf entire solar systems. Matter, compressed beyond all recognition, can disappear into regions where space and time lose their familiar meanings. TON 618 embodies those extremes without apology or explanation. It simply exists, reshaping its corner of the universe through the patient application of physical law. Its story continues even now, billions of years after the light we see today first began its journey toward Earth. Somewhere in that ongoing narrative, between measurement and mystery, lies something profound about the nature of cosmic scale and our place within it. When we try to grasp something like TON 618, we're really trying to understand our place in a universe that operates on scales beyond our everyday experience. This quasar sits billions of light years away, quietly demonstrating just how vast and how organized the cosmos can be. The universe has a peculiar way of building its most extreme objects. Nothing starts out massive. Everything begins small, accumulating piece by piece, over time spans that dwarf human history. Black holes follow this same patient process, even though their final forms can seem almost impossible to believe. At the heart of every black hole lies a story of stellar death. When massive stars run out of fuel, they face a moment of reckoning. The nuclear fires that kept them burning suddenly die out, and gravity takes complete control. The star collapses inward, crushing matter into densities that seem to break the rules of ordinary physics. Most of the time, this creates something relatively modest. A stellar black hole, perhaps 3 or 4 times heavier than our Sun. These objects start their lives quietly, almost invisibly, waiting in the darkness for something to come within reach. The transformation from modest to monstrous happens through feeding. Black holes don't simply gobble up everything around them like some cosmic vacuum cleaner. Instead, they create elaborate dining arrangements. When matter gets too close, it doesn't fall straight in. Gravity pulls it into a spiraling dance, forming what astronomers call an accretion disk. This disk becomes a theater of extreme physics. As gas and dust spiral inward, they compress and heat up to temperatures that would vaporize any material we know. The friction between particles converts motion into thermal energy, and that energy radiates outward as light and X-rays. It's this radiation that makes quasars like TON 618 visible across the universe. The physics governing this process reveals something almost philosophical about nature's tendency toward balance. Gravity pulls matter inward, but the intense heat and radiation push outward. These opposing forces find an equilibrium point, known as the Eddington limit, where a black hole can feed as fast as physics allows without disrupting its own meal. TON 618 appears to operate right at this limit, consuming matter as efficiently as the laws of nature permit. It's eating at the theoretical maximum, a cosmic entity pushing against the boundaries of what's physically possible. But black hole growth isn't always so orderly. In the early universe, galaxies were smaller, denser, more chaotic places. Gas clouds collided regularly, stars wandered closer to galactic centers, and entire galaxies merged with one another. During these violent events, black holes could experience sudden growth spurts, doubling or tripling in mass almost instantaneously. Each increase in mass makes the black hole's gravity stronger, which makes it easier to capture more material. It's a self-reinforcing cycle that can transform a modest stellar remnant into a supermassive giant over cosmic time. For TON 618 to reach its staggering proportions, it must have experienced several of these feeding frenzies early in cosmic history. The relationship between a black hole and its host galaxy resembles a strange kind of partnership. As the black hole feeds, it releases enormous amounts of energy that can affect star formation throughout the galaxy. Too much activity can actually shut down the feeding process by pushing away nearby gas clouds. Too little, and the black hole begins to fade from view. This creates a natural regulatory system where black holes and galaxies influence each other's evolution. The black hole shapes the galaxy by controlling how and where new stars can form. The galaxy, in turn, provides the raw material that determines how large the black hole can grow. The image of black holes as purely destructive forces misses half the story. While it's true that nothing can escape once it crosses the event horizon, most matter never reaches that point. Much of it gets heated, accelerated, and eventually ejected back into space through powerful jets that can stretch thousands of light years. These jets represent one of nature's most efficient energy conversion systems. The rotational energy of the black hole, combined with magnetic fields in the accretion disk, accelerates particles to nearly the speed of light. Through these outflows, black holes return energy to the universe, influencing the formation of stars and galaxies far from their immediate neighborhood. There's something almost poetic about this cycle. Matter falls toward annihilation, but in doing so, it creates the very energy that can trigger new star formation elsewhere. The light from TON 618's feeding process has traveled billions of years to reach our telescopes, carrying information about physical processes operating under the most extreme conditions imaginable. When scientists model how supermassive black holes grow, they consider several possible pathways. Steady accretion provides consistent but slow growth. Galaxy mergers can suddenly double a black hole's mass. Under special circumstances, black holes might temporarily exceed the Eddington limit, experiencing rapid growth spurts that conventional physics suggests shouldn't be possible. The dense, chaotic environment of early galaxies probably allowed for all these processes to occur simultaneously. Young galaxies were messier places, with more available fuel and fewer stable structures to regulate the feeding process. This could explain how objects like TON 618 managed to grow so large in the relatively short time since the universe began. What's remarkable is that even under these extreme conditions, black hole feeding follows predictable physical laws. The same equations that describe how planets form from dust disks around young stars also govern how matter spirals into black holes. The scale differs dramatically, but the underlying principles remain constant. This consistency reveals something profound about the nature of physical law. The universe doesn't switch rule sets when dealing with different scales or energies. Gravity behaves the same way whether it's organizing solar systems or powering quasars. Heat transfer, magnetic fields, and fluid dynamics operate according to the same principles in accretion disks as they do in earthbound laboratories. If you could somehow observe TON 618 up close, you wouldn't witness chaos in any human sense of the word. You'd see elegant patterns emerging from mathematical relationships, gas following predictable orbital paths, temperatures increasing smoothly toward the center, radiation obeying precise spectral laws. The light we detect from this distant quasar represents the end product of these orderly processes, predictable and measurable despite the extreme energies involved. Each photon carries encoded information about magnetic field strengths, gas temperatures, and orbital velocities operating around a black hole, billions of times more massive than our Sun. This reliability of physical law across such vast scales and energy ranges suggests something fundamental about the universe's structure. The same forces that bind atoms in our bodies also govern the behavior of matter falling into supermassive black holes. The same principles that determine how heat flows through a cup of coffee also describe energy transport in quasar accretion disks. Perhaps this is what makes objects like TON 618 so intellectually compelling. They represent familiar physics pushed to absolute extremes, revealing aspects of natural law that remain hidden under ordinary conditions. By studying these cosmic giants, we're discovering new facets of the same physical reality that shapes our daily experience. The universe operates on principles that seem almost impossibly consistent, playing out the same fundamental rules across spans of time that dwarf human comprehension. When we look at the most massive black holes in existence, we're witnessing this consistency in action, watching how gravity and energy dance together in ways that have remained unchanged for billions upon billions of years. These cosmic giants don't simply grow without limits, though. They go through phases, much like living things do. During their most active periods, they feed voraciously on the gas and matter surrounding them, creating some of the brightest objects we've ever observed. But eventually, their local supply runs out. The galaxy around them becomes depleted of the material they need to sustain their incredible energy output. When this happens, they essentially go quiet, becoming invisible to most of our instruments, detectable only through the way they bend space around them. What's fascinating is that the light we see from these distant feeding frenzies today might be showing us black holes that went silent long ago. The photons reaching our telescopes left their sources when the universe was much younger. By now, those same black holes might be dormant, their spectacular light shows having ended eons ago. We're looking at cosmic history, watching events that played out when time itself was still relatively young. There's something almost poetic about how black holes, despite their reputation as cosmic destroyers, actually serve as regulators in the universe's grand design. They don't just consume everything around them endlessly. Instead, they help distribute energy and matter throughout space, preventing galaxies from becoming too densely packed. Without this regulatory effect, the cosmos might have evolved into something completely different, perhaps too crowded and unstable to support the kind of ordered structure we observe today. This regulatory function happens through a process that's surprisingly efficient. When matter spirals into a black hole, it doesn't all disappear beyond the event horizon. Much of it gets heated to incredible temperatures and expelled back into space through powerful jets and winds. These outflows carry energy far from the black hole, spreading it across vast distances and influencing how new stars form in the surrounding region. The efficiency of this process is staggering when you compare it to other cosmic phenomena. Stars, for all their nuclear fusion power, convert less than 1% of their mass into energy. Black holes, during their active feeding phases, can convert up to 40% of incoming matter into pure energy. This makes them the most efficient engines we know of in the natural world, capable of outshining entire galaxies while remaining essentially invisible themselves. This efficiency explains how we can detect these objects across such enormous distances. The light they produce during their feeding phases is so intense that it can travel for billions of years and still reach us with enough strength to be analyzed in detail. Every photon carries information about the conditions near the black hole. The temperature of the surrounding gas, the speed at which matter was moving, the amount of energy being released. It's like receiving a detailed report from the most extreme environments in the universe. Astronomers have discovered something remarkable about the relationship between black holes and their host galaxies. The mass of a galaxy's central black hole correlates closely with the mass of the galaxy's central bulge, that dense region of stars at its heart. This isn't coincidence. It suggests a feedback loop that operates over cosmic timescales. As the black hole feeds and grows, it influences star formation throughout the galaxy. As stars form, live, and die, they return material that can eventually feed the black hole. Each process depends on the other, creating a cycle that spans billions of years. This relationship raises intriguing questions about limits and boundaries. Could a black hole theoretically grow forever, or are there natural constraints that eventually halt their expansion? In principle, as long as there's matter to consume, a black hole could continue growing indefinitely. But the universe itself places practical limits on this process. As cosmic expansion continues, galaxies drift apart from each other, and the supply of new material available to any given black hole gradually diminishes. Eventually, even the most massive black holes will exhaust their local fuel supply. When that happens, they'll enter a phase of cosmic dormancy that could last longer than the current age of the universe. They'll remain gravitationally influential, still capable of affecting nearby objects, but their days as brilliant beacons will be over. They'll become cold, quiet, and essentially eternal. Monuments to forces that once shaped entire galactic neighborhoods. The temporary nature of their brilliance, on cosmic scales, makes their current activity all the more remarkable. While they shine, these objects represent some of the most energetic processes happening anywhere in the universe. They're converting matter to energy with an efficiency that surpasses every other natural phenomenon we've discovered. In a very real sense, they're the ultimate factories of light, even though the black holes themselves emit no light at all. This paradox, darkness creating brightness, reflects something deeper about how the universe organizes itself. The same gravitational forces that make black holes invisible also power the mechanisms that make them detectable across billions of light years. It's gravity that accelerates matter to incredible speeds, heating it until it glows brighter than entire stellar populations. The event horizon that defines the point of no return also defines the boundary where this incredible energy production takes place. As we study these distant giants, we're really studying the universe's capacity for self-organization. Black holes don't exist in isolation. They're integral to galactic evolution, determining where stars can form, how long galaxies remain active, and how energy circulates on the largest scales we can observe. Their presence shapes the very architecture of cosmic structure, influencing processes that span from the quantum scale to the scale of galaxy clusters. Every galaxy we've studied in sufficient detail contains a supermassive black hole at its center. Each one tells a similar story of growth, balance, and transformation through consumption. They represent both endpoints and catalysts in the cosmic recycling of matter. Material that gets expelled during their feeding phases doesn't disappear. It eventually cools, disperses, and becomes available for new generations of star formation, potentially in completely different regions of space. The atoms swirling near a black hole's event horizon today might, billions of years from now, become incorporated into new planetary systems in distant galaxies. The cycle continues indefinitely, matter changing form but never truly disappearing. Even in what appears to be destruction, there's an underlying continuity that connects every part of the cosmic story. This perspective transforms how we think about these extreme objects. They're not cosmic monsters devouring everything in sight. They're more like cosmic recyclers, processing matter and energy in ways that make new growth and development possible elsewhere. The same principles governing their behavior, gravity pulling inward while energy pushes outward, operate throughout the universe at every scale we can observe. When we analyze the light from these distant feeding events, we're participating in a process that's been happening since the universe was young enough for the first massive stars to collapse. Matter becomes energy, energy becomes light, light becomes knowledge. Through careful observation and patient analysis, we become part of this cosmic conversation, reading messages written in radiation across timescale that dwarf human civilization. Perhaps that's what makes studying these objects so compelling. They connect us to the fundamental processes that shape everything we observe, from the largest galactic structures down to the chemistry that makes life possible. The same forces that power their incredible energy output also govern stellar formation, planetary development, and the distribution of elements throughout space. In trying to understand how black holes grow and evolve, we're really trying to understand how the universe builds itself, one particle at a time, across billions of years of cosmic time. When we peer into the cosmic depths toward 2618, we're looking at something that defies our most basic assumptions about reality. All that brilliant light, all that scorching heat radiating outward, none of it actually comes from the black hole itself. The monster at the center sits in perfect, eternal silence. What we call a black hole isn't really a thing at all, not in any way we normally think about objects. It's more like a wound in the fabric of everything, a place where space and time curve so dramatically that they fold back on themselves. Imagine trying to walk in a straight line, only to find that straight lines don't exist anymore. That every path you take leads you deeper into a spiral you never intended to follow. The mathematics tell us that light itself, which always travels in perfectly straight lines, gets caught in these curves around 2618. Photons can actually orbit the black hole multiple times, like cars on a cosmic racetrack, before finally disappearing forever into the darkness. It's a strange thought that light can be trapped, considering how we think of it as the fastest, most unstoppable force in nature. At the edge of this cosmic trap sits something called the event horizon. It's not a physical wall or barrier, more like an invisible line drawn in space-time itself. Cross that line, and you're cut off from the rest of the universe forever. But here's where things get really peculiar. If you were watching someone fall toward that boundary, they would appear to slow down, getting slower and slower until they seem to freeze completely at the edge, their image fading to red and then to nothing. To the person falling, though, nothing strange happens at all. They cross the line in normal time, continuing their journey inward. Both perspectives are completely accurate, which tells us something profound about the nature of reality itself. There isn't just one version of events, one universal truth. Your experience of time and space depends entirely on where you happen to be standing in the universe. Near 2618's heart, gravity doesn't just pull on matter, it actually reshapes the flow of time. Clocks run slower the closer you get to that enormous mass. If you could somehow hover near the event horizon, safe from being pulled in, your watch would tick at a completely different rate than a watch here on Earth. The difference would be so extreme that while you experienced a few seconds, decades, or even centuries might pass in the outside universe. This isn't science fiction or theoretical speculation. We've measured this effect around Earth, around our Sun, even around neutron stars. Time really does slow down in strong gravitational fields. 2618 just takes this everyday phenomenon and stretches it to surreal extremes. You could watch the universe outside age and evolve in fast forward while observers far away would see you moving in slow motion, almost frozen in time. Once you cross the event horizon, something even stranger happens. All directions, even the ones that should lead back out to space, now point inward toward the center. It's not that some force is pulling everything in, it's that the geometry of space-time itself has been bent so far that inward is the only direction that exists anymore. At the very center of 2618 lies what physicists call a singularity. This isn't a place you could visit, or a thing you could touch. It's a mathematical concept that represents something almost impossible to grasp. The mass of 66 billion suns compressed into a space smaller than an atom. When we try to imagine what that means, our everyday understanding of matter and space simply breaks down. The singularity marks the edge of human knowledge, the point where our best theories stop working and start giving us answers that don't make sense. It's like trying to divide by zero. The mathematics becomes meaningless. This doesn't mean nothing exists there, just that we don't yet have the tools to understand what that something might be. Scientists hope that someday a theory of quantum gravity might explain what really happens in these extreme conditions. For now, we can only say that the core of TON 618 represents the most extreme environment possible in our universe, where density and temperature reach values that stretch our imagination to its limits. When matter spirals into the black hole, it accelerates to nearly the speed of light. The friction between particles creates incredible heat, releasing enormous amounts of energy as radiation. The closer this material gets to the event horizon, the more energy it releases, until finally that energy can't escape either. From our distant perspective, we see the infalling matter slow down, dim, and fade away, never quite seeming to cross the line. But that's just a trick of light and time. In reality, that matter crosses quickly and disappears into a future that remains forever hidden from us. The interior of a black hole is completely cut off from the rest of existence. No information, no signal, no particle can ever return to tell us what happens inside. Yet somehow, the black hole continues to influence everything around it through gravity. The mass it contains keeps shaping space-time, affecting the motion of stars and gas across vast distances. It's both completely isolated and intimately connected to the universe around it, like a secret that shapes everything while remaining forever untold. The event horizon itself changes over time. When TON 618 consumes new material, its boundary grows larger, expanding outward in proportion to the added mass. Over billions of years, this monster has likely grown through countless feeding events, each one making it larger and more powerful than before. Even this seemingly absolute boundary might not be perfectly smooth. Quantum mechanics suggests that the event horizon could fluctuate at the smallest scales, rippling with tiny variations due to the fundamental uncertainty that governs all matter and energy. Stephen Hawking's work revealed that black holes might not be entirely black after all, that they could emit faint radiation through quantum processes near the horizon. For something as massive as TOT 618, this Hawking radiation would be incredibly weak, far too faint to detect. But in theory, it means that even this cosmic giant could slowly evaporate over unimaginably long time periods. The process would take far longer than the current age of our universe multiplied by itself countless times, but it reminds us that even the most permanent features of our cosmos might not be eternal, after all. The universe operates on principles that remain constant whether we're examining a pebble or the most massive objects ever discovered.
TON 618 demonstrates this beautifully.
The mathematics describing its core are surprisingly elegant. The Schwarzschild radius formula depends only on mass and a few fundamental constants. Double the mass and you double the radius. Simple as that. The same equation works for black holes weighing 3 times our Sun or 66 billion times our Sun. Scale changes everything, yet changes nothing at all. This reveals something profound about nature's architecture. Even at the most extreme boundaries, the rules stay the same. It's like finding that the same blueprint governs both a cottage and a skyscraper. The materials are identical: hydrogen and helium, the same stuff that built every star and planet we know. Nothing exotic in the ingredients. Only the conditions differ. Under enough pressure, matter stops being matter as we understand it. It becomes pure geometry. Instead, picture trying to navigate toward the center of TON 618. There are no stable orbits waiting for you. No escape routes either. Just continuous falling towards something that might not exist as a place at all. The deeper you travel, the more the concept of location dissolves completely. Instead of arriving somewhere, you encounter inevitability. Space itself gets replaced by curvature. The notion of a center becomes meaningless because you're not moving through space anymore. You're following the shape that space has become. From outside, TON 618 appears as energy and motion perfectly balanced. Light, radiation, gravity, all in cosmic harmony. From inside, if experience were possible there, it would be pure geometry. No landmarks, no directions, no familiar reference points. The manifestation of gravity's final form, what happens when matter's pressure finally surrenders to collapse. Everything visible around it, the blazing accretion disk, the massive jets, the intense radiation, these are just byproducts. Side effects of invisible geometry, doing what geometry must do. The event horizon creates something remarkable, a one-way membrane between known and unknown. It's the boundary of knowledge itself. Information crosses inward freely, but cannot return outward ever. This creates one of physics' greatest puzzles, the information paradox. Quantum theory insists that information about any system state can never be destroyed completely. Yet matter and light disappear into black holes without sending back any reports. Where does that information go? Some physicists propose the horizon stores everything holographically, data smeared across its surface like a cosmic hard drive. Others suggest quantum entanglement preserves information in ways we haven't detected yet. TON 618's enormous scale magnifies this question tremendously. Whatever answer emerges will reshape our understanding of reality's fundamental nature. The implications stretch far beyond astronomy into the heart of what existence means. There's something philosophically striking about this barrier. No matter how powerful our instruments become, certain limits cannot be crossed. The laws of nature themselves establish boundaries on knowledge. The event horizon isn't just a physical obstacle, it's an epistemological one. A reminder that understanding has edges. Beyond those edges lie speculation, mathematics, imagination. Perhaps the existence of such frontiers gives science its depth. Without limits, discovery would lose all meaning. Even so, the region surrounding the horizon overflows with measurable phenomena. Gravitational lensing bends light from background galaxies into perfect arcs and rings. X-rays from the inner disk reveal particles moving at relativistic speeds. Radio emissions trace magnetic fields twisted by rotation. Each signature lets astronomers map the invisible through its effects. Turning absence into data, one photon at a time, what emerges is not chaos, but remarkable elegance. TON 618's heart, despite its violence, maintains perfect stability. Spherical symmetry governs it. Predictable behavior across time, it doesn't flicker like stars do. It endures with absolute consistency. Its gravity is devastating but precise. Space curves smoothly inward following exact mathematical laws. Light travels defined paths. Energy radiates according to fixed principles. The monster's heart isn't wild at all. It's possibly the universe's most orderly creation. That mathematical perfection carries quiet beauty. The equations are exact, clean, deceptively simple. This strange harmony persists, even at cosmic extremes. If you could drift near the event horizon and look outward, you'd witness a completely distorted universe. Distant starlight would bend around you, circling the black hole before escaping. The outside world would compress into a bright ring surrounding darkness. The sky would fold in on itself, wrapping a 360-degree view around your vision. Looking back toward the center would reveal absolutely nothing. Pure blackness, where geometry ends. Not death or emptiness in any emotional sense. Simply a place where our definitions of existence no longer apply. This challenges fundamental concepts. What does place mean when location dissolves? What does inside mean when space curves completely inward? What does time mean when causality flows only one direction? The universe isn't obligated to be intuitive. Nature follows discoverable rules, but not always visualizable ones. A black hole's center wasn't designed to fit comfortably within human imagination. Standing at this realization's edge, we feel simultaneously small and oddly connected. The same physics governing that incomprehensible heart also governs everything around us. The morning coffee cooling on your table follows the same thermodynamic principles that drive matter toward event horizons. Perhaps most astonishing is recognizing that TON 618's core contains nothing more exotic than ordinary matter. Hydrogen and helium compressed beyond all recognition. The universe recycles materials everywhere, changing only the conditions. Under sufficient pressure, matter transforms into geometry, and geometry becomes destiny. This hidden heart shapes everything visible around it. Its gravity anchors entire galaxies. Its energy fuels brilliant emissions across space. Its silence, paradoxically, gives rise to light. In this balance between visibility and absence lies something essential about cosmic nature. The greatest forces often remain invisible. The most powerful truths can only be inferred, never directly observed. The monster's heart isn't merely a mystery awaiting solution, it reflects how far knowledge can extend before yielding to wonder. Even in darkness's center, structure persists. Even in gravity's ultimate expression, perfect balance endures. The cosmos speaks in whispers that never truly stop. Throughout the endless darkness, energy moves in patterns we can barely imagine, carrying messages from places so distant they might as well be from another lifetime. Radio waves drift between stars, light stretches across impossible distances, and gravitational ripples move through space itself, all of them telling stories about things that happened when the universe was fundamentally different than it is today. Every single event that occurs in space, no matter how remote, leaves its mark on the fabric of everything around it. When massive objects collide, when stars explode, when matter spirals into black holes, they all create disturbances that spread outward like ripples on an infinite pond. These disturbances never completely disappear, they just get fainter and fainter as they travel. But they remain detectable if you know how to listen for them. Think about how strange this really is. Right now, photons of light that began their journey billions of years ago are reaching Earth, carrying information about events that happened before our solar system even existed. Some of these photons started traveling when the universe was less than half its current age, when galaxies looked completely different, when the very structure of cosmic space was more compact and energetic than anything we see today. The light doesn't arrive with any kind of identification tag attached to it. When astronomers point their telescopes toward distant objects, they're essentially catching faint signals that have been stretched and modified by their incredibly long journey through expanding space. What started as one type of radiation billions of years ago might arrive as something completely different. Shifted toward longer wavelengths, dimmed by distance, mixed with countless other signals from countless other sources. Scientists have to work like cosmic detectives, separating these overlapping signals, analyzing their properties, figuring out which wavelengths belong to which distant objects. It's remarkably similar to trying to identify individual conversations in a crowded room, except the room is the entire observable universe, and some of the conversations started before Earth existed. Radio astronomy opened up entirely new ways of listening to these cosmic whispers. In the middle of the 20th century, researchers began mapping the sky using radio telescopes, and they discovered something unexpected. There were sources of radio emission that appeared to be coming from single points in space, but these points were incredibly bright, far brighter than any individual star should be able to produce. These mysterious radio sources didn't match anything astronomers had seen before. They appeared star-like through optical telescopes, but their radio emission suggested they were something much more powerful and distant. Scientists called them quasi-stellar objects, because they seemed to combine the appearance of stars with properties that no star could possibly have. One of these objects was catalogued at an observatory in Mexico and given the designation TON 618. At the time, it was just another entry in a growing list of strange radio sources. Nobody realized they were looking at echoes from some of the most extreme objects in the entire universe, powered by black holes so massive they defy easy comprehension. The light from these distant objects wasn't constant. It flickered and varied over periods of weeks, months, and years. This variability was actually a crucial clue. because it told astronomers something important about the size and nature of these mysterious sources. If an entire galaxy was producing this light, it couldn't vary so quickly, because galaxies are enormous, and it takes time for changes to spread across such vast distances. But if the light was coming from something much smaller, something concentrated in a tiny region of space, then rapid variations would be possible. The pattern of these fluctuations, combined with other measurements, pointed toward a remarkable conclusion. These quasi-stellar objects were actually the incredibly bright centers of distant galaxies, powered by supermassive black holes that were actively feeding on surrounding matter. When matter falls toward a black hole, it doesn't just disappear quietly. It forms a swirling disk of superheated gas that glows with intense radiation across multiple wavelengths. This accretion disk can outshine the entire rest of the galaxy, making the central black hole visible across billions of light-years of space. The flickering that astronomers observed was actually the changing brightness of this feeding process, as the black hole consumed varying amounts of material. Modern astronomy uses instruments that can detect many different types of electromagnetic radiation simultaneously. Radio telescopes pick up the low-frequency signals from massive jets of particles that some black holes shoot into space. Optical telescopes capture the stretched light from the glowing accretion disk itself. X-ray satellites orbiting above Earth's atmosphere record the high-energy radiation produced when matter gets torn apart just before crossing the black hole's event horizon. Each of these different wavelengths reveals a different aspect of the same cosmic phenomenon. Radio waves tell us about the jets. Optical light shows us the disk. X-rays reveal the most violent processes happening near the black hole itself. Together, they create a comprehensive picture of something we could never observe directly. This process of cosmic listening represents one of humanity's most subtle achievements. The amount of energy that reaches us from these distant objects is almost incomprehensibly small. We're talking about a few photons per square meter per second, spread across the entire cross-section of our planet. Yet with carefully designed instruments, scientists can detect these faint signals, measure their properties, and extract detailed information about objects that are billions of light-years away. The light that reaches us has been traveling for most of the age of the universe, growing weaker with every passing moment, but never losing the encoded information it carries. Within those faint photons, astronomers can read the chemical composition of the gas surrounding distant black holes, measure the speed at which that gas is moving, and even determine how fast the black holes themselves are spinning. Astronomy is fundamentally a science of patience and deduction. We can't visit the objects we study, can't collect physical samples, can't perform direct experiments. All we can do is collect light, analyze it carefully, and figure out what it tells us about the distant sources that produced it. From this analysis, entire cosmic stories emerge. A pattern of bright and dark lines in the spectrum becomes evidence for specific chemical elements heated to millions of degrees. A systematic shift in wavelength becomes proof that a galaxy is moving away from us due to cosmic expansion. A subtle change in brightness over time becomes the signature of matter spiraling into a black hole. The most distant objects provide the most ancient information because light travels at a finite speed. When we observe something billions of light-years away, we're seeing it as it was billions of years ago, when the universe was younger, denser, and more active than it is today. These observations give us direct access to cosmic history, allowing us to study how the universe has changed over time. The early universe was a very different place than the cosmos we see around us now. Galaxies were smaller and more active. Black holes were feeding more voraciously, and bright quasars were much more common than they are today. By studying the light from these ancient objects, astronomers can piece together the story of how the universe evolved from its turbulent youth to the more settled state we observe in the present day. Spectroscopy is the fundamental technique that makes this cosmic archaeology possible. When light passes through hot gas, specific wavelengths get absorbed, creating dark lines in the spectrum that serve as fingerprints for different chemical elements. By analyzing these spectral lines, scientists can determine not just what elements are present, but their temperature, density, and motion. When astronomers spread starlight into its component colors, They unlock secrets written in the language of atoms. Each element leaves its own signature, its own fingerprint, embedded in the spectrum. Hydrogen creates one pattern, oxygen another, carbon yet another. These lines of light and shadow tell stories that stretch across billions of years. What makes this even more remarkable is how motion reveals itself through color. When something moves away from us, its light gets stretched, shifted toward the red end of the spectrum. It's like listening to a train whistle fade into the distance, except we're dealing with waves of light instead of sound. This stretching happens because space itself expands, carrying distant objects away from us at incredible speeds. The further something is, the more its light gets stretched. By measuring this shift, scientists can calculate distance with surprising precision. Some objects are so far away that their light has been traveling toward us for over 10 billion years. We're seeing them as they were when the universe was young, wild, and very different from today. But visible light is just one way the cosmos speaks to us. Radio waves offer another conversation entirely. These longer wavelengths can travel vast distances without getting scattered or absorbed. They carry messages from some of the most energetic processes in the universe, events so powerful they boggle the imagination. Near the edge of a massive black hole, magnetic fields get twisted into incredible configurations. The black hole's spin winds these fields tighter and tighter until they snap, launching jets of particles at nearly the speed of light. These jets shoot out from the poles, creating beams that can stretch for millions of light years across space. When these high-speed particles slam into surrounding gas and dust, they create enormous radio-emitting regions. These structures are so large that our entire galaxy would fit comfortably inside just one of them. By mapping the radio emissions, astronomers can trace the shape and power of these invisible monuments to cosmic violence. Even more exotic signals might be traveling toward us. Gravitational waves, ripples in the fabric of space and time itself, carry information about the most dramatic events possible. When two massive black holes spiral into each other and merge, they create vibrations that propagate across the universe like waves on a cosmic pond. We haven't yet detected these signals from the most distant sources, but future instruments might catch them. Each new type of observation adds another sense to our cosmic perception. We're gradually learning to see, hear, and feel the universe in ways our ancestors never imagined. What strikes me as profound is how these messages persist. In our daily lives, everything seems permanent. The same stars shine overhead night after night. Constellations maintain their patterns year after year. But this apparent stillness is an illusion created by the vast scales involved. In cosmic time, everything changes constantly. Galaxies dance together and collide. Stars explode in brilliant death throes. Black holes grow by consuming everything around them, then eventually fade as the universe ages. The light we see from distant objects shows us single moments frozen in this grand choreography. Right now, in the present moment, these distant objects might look completely different. They could be quiet, dormant, or transformed beyond recognition. Yet their ancient light continues traveling toward us, carrying news of events that ended eons ago. Light doesn't know or care when it was created. It simply moves forward at its constant speed, carrying information until something intercepts it. We happen to be the interceptors, the final destination for photons that have been traveling since before Earth even existed. Our telescopes are essentially time machines, collecting the last remnants of events that occurred when the universe was a very different place. This creates a strange kind of translation process. Gravity and energy create disturbances that generate light. That light travels across impossible distances and arrives at our detectors as data. We then convert that data into images, graphs, and mathematical models. Finally, through careful analysis, we transform it into understanding. The whole process connects us to phenomena that should be completely beyond our reach. We cannot visit these distant places or send probes to investigate them directly. But through light and other forms of radiation, we can reconstruct their stories with remarkable detail. Perhaps the most humbling aspect is how faint these signals actually are. When photons finally reach Earth after traveling for billions of years, they arrive stretched and weakened by their journey. They're individual packets of energy scattered among countless others, from stars, galaxies, and cosmic dust throughout the universe. By gathering these whispers patiently, over years of observation, we can separate meaningful signals from background noise. A telescope doesn't see distant objects in any traditional sense. Instead, it collects their faintest communications and amplifies them through mathematics and technology. These cosmic echoes reveal how thoroughly connected everything is. The same space that carries light from the most distant galaxies also carries the afterglow of the Big Bang itself. The same vacuum that allows radio waves to travel also transmits cosmic rays, neutrinos, and gravitational effects. Each type of signal operates at its own scale and energy level, but all share the same cosmic stage. The universe isn't empty space punctuated by objects. It's more like a medium filled with overlapping communications, every part resonating with the motion of everything else. The discovery of extremely distant, powerful objects fundamentally changed how we think about cosmic structure. Before these discoveries, the universe seemed relatively quiet beyond our local neighborhood. Galaxies existed, but few scientists imagined that their central regions could outshine hundreds of billions of stars combined, realizing that these brilliant beacons were powered by supermassive black holes billions of light years away, expanded not just our catalog of cosmic objects, but our entire understanding of how the universe works. It demonstrated that even in apparently empty regions, incredible energy and motion persist. Every signal we receive contributes to a collective memory of cosmic history. Each spectrum, each radio wave, each flicker of high-energy radiation adds another piece to the puzzle. When we convert these signals into visual representations and mathematical models, we're essentially tuning into frequencies that resonate across time itself. The raw power of distant black holes, stretched and softened by distance and time, reaches us as a gentle stream of data. Within that stream lies encoded information about matter transforming into energy, gravity warping space, and the universe expressing its fundamental forces through form and motion. Even the background static in our most sensitive detectors holds meaning. Some of that noise comes from the edge of the observable universe. Some originates from ancient stars that died before our solar system formed. Some comes from distant powerhouses whose signals have blended into cosmic background radiation over billions of years. This reminds us that apparent silence in space isn't emptiness at all. It's complexity stretched, thin across enormous scales. The universe behaves like an ocean that looks calm from the surface, but contains currents and waves of every possible size and rhythm, each carrying stories of motion and change. The most powerful black holes are like great storms in that cosmic ocean, sources of disturbances that continue spreading across billions of light years. We, tiny observers on a small planet, have somehow become sensitive enough to detect these incredibly faint ripples. We've built instruments to measure them, learned to interpret their patterns, and discovered meaning in their rhythm. The fact that we can detect something so distant and ancient from quiet observatories on Earth might seem impossible, but it demonstrates how far human perception has expanded. We've learned to amplify the faintest cosmic whispers and translate them into knowledge. In doing so, we've transformed the cosmos into a kind of dialogue, not of words, but of waves and particles. Distant black holes speak in this universal language, their messages carried by light and energy across distances that dwarf human comprehension. The echoes continue, faint but persistent, threading through space like invisible currents. They remind us that even in the vast emptiness between galaxies, everything remains connected through motion, energy, and time. Light from the most distant objects mingles with radiation from nearby stars and the relic heat left over from cosmic creation itself. We're surrounded by these echoes constantly, bathed in ancient light without always realizing it. Somewhere among the countless photons reaching Earth every second, a few carry news from black holes that formed when the universe was young. These messengers bring with them the silent memory of power and violence beyond imagination. translated into the gentle language of light that our instruments can finally understand. The cosmos operates on scales that stretch our understanding, where measuring becomes an act of interpretation rather than simple observation. When we encounter something like TON 618, we're not just looking at numbers, we're confronting the limits of what it means to know something exists. This black hole forces us to reimagine measurement itself, transforming it from a mechanical process into something closer to detective work. Light becomes our primary witness in this investigation. Every photon that reaches our instruments has traveled for billions of years, carrying information encoded in ways that require careful decoding. The brightness we detect tells us about energy output, but that brightness has been stretched and shifted by the expansion of space itself. What we see is not what was originally emitted, but rather a transformed version, aged by time and distance. The process starts with apparent magnitude, how bright the object appears from Earth. TON 618 sits far beyond what human eyes can detect, requiring sensitive instruments to capture its faint signal. But that faintness is deceptive. Once astronomers account for distance, the true luminosity emerges, revealing an object that outshines entire galaxies. This quasar pumps out energy equivalent to about 100 trillion suns, a figure that pushes against the boundaries of what physics allows. That luminosity creates a puzzle that leads directly to mass estimates. Such enormous brightness requires an equally enormous engine to power it. The Eddington limit provides the key here, describing the delicate balance between a black hole's gravitational pull and the radiation pressure of its glowing accretion disk. If radiation becomes too intense, it blows away the very material feeding the black hole. This natural ceiling means that only the most massive objects can sustain such incredible brightness over long periods. Working backwards from luminosity through efficiency estimates of matter-to-energy conversion, astronomers arrive at mass figures that seem almost fictional. Roughly 66 billion solar masses concentrated into a region smaller than our solar system. The calculation depends on assumptions about how efficiently matter converts to energy as it spirals inward, typically around 10% for rotating black holes. Even small changes in these assumptions affect the final number, but the result consistently places TON 618 among the most massive objects ever discovered. Spectral analysis adds another layer to this cosmic archaeology. The light from TON 618 contains broad emission lines, signatures of hydrogen and other elements moving at tremendous speeds near the black hole. These lines appear smeared across the spectrum because the gas producing them moves at different velocities depending on its distance from the gravitational source. Some material approaches us, blue shifting its light, while other material recedes, red shifting it. The width of these spectral lines reveals orbital velocities reaching several percent of light speed. Only an immense gravitational field could maintain such speeds, without flinging matter into deep space. By modeling these velocities against theoretical predictions for gas orbiting massive objects, astronomers can work backwards to the mass required to produce such motion. The calculations consistently support the enormous mass estimates derived from luminosity measurements. Reveration mapping provides yet another approach to measuring the unmeasurable. This technique exploits the fact that brightness variations in the inner accretion disk create delayed responses in surrounding gas clouds. As the central region fluctuates, those changes ripple outward at light speed, causing echoes in the broader emission. The time delay between original signal and echo reveals the physical size of the system. For TON 618, these delays span timescales that correspond to structures extending across light years. The size, combined with velocity measurements from spectral line widths, allows astronomers to calculate the gravitational influence required to organize matter across such vast scales. Multiple independent methods converging on similar mass estimates strengthens confidence in results that would otherwise seem impossible to verify. Distance presents its own measurement challenges. When we say TON 618 lies 10.4 billion light-years away, we're describing look-back time, how long its light has traveled to reach us. But space itself has expanded during that journey, stretching the wavelengths and increasing the actual distance. The redshift value of 2.219 provides the key to unraveling this cosmic geometry. Redshift occurs when expanding space stretches light waves, pushing them toward longer, redder wavelengths. The amount of stretching depends on how much the universe has expanded since the light was emitted. Cosmological models, incorporating our best understanding of cosmic expansion rates, translate redshift into both look-back time and commoving distance. The result places TON 618 at a time when the universe was roughly 2 billion years old, less than 20% of its current age. This temporal perspective adds profound context to every measurement. We're not observing TON 618 as it exists today, but as it appeared when the cosmos was young and galaxies were still forming. The black hole we study represents an early chapter in cosmic evolution, a time when conditions were dramatically different from what we see in the nearby universe. Every photon carries information from that ancient era, making our observations into a form of time travel. The technical challenges of observing such distant objects push astronomical instruments to their limits. The signal is incredibly faint after traveling such vast distances, requiring long exposure times and careful noise reduction. Interference from nearer galaxies, atmospheric distortion, and instrumental effects all need correction before the true properties emerge. What appears as a simple point of light in images actually represents the combined effort of multiple telescopes, sophisticated data processing, and decades of accumulated observations. Survey programs contribute most of the data used to characterize objects like TON 18. These systematic sky surveys collect information over many years, building up detailed records of brightness variations and spectral properties. No single observation captures everything needed for complete characterization. Instead, the full picture emerges from careful combination of multiple datasets, each contributing pieces to the larger puzzle. Uncertainty remains an honest part of this process. The mass of TON 618 might be 60 billion solar masses, or 70 billion depending on which assumptions prove most accurate. Different measurement techniques yield slightly different results, each carrying its own sources of error. But this uncertainty doesn't undermine the fundamental conclusion that we're dealing with something extraordinary. Whether the exact number is 60 or 70 billion, the scale remains almost incomprehensible. The philosophical implications run deeper than the technical challenges. Astronomical measurement requires faith in the universality of physical laws. The same gravity that affects objects on Earth must operate identically around a black hole billions of light years away. The same atomic physics that produces spectral lines in laboratory experiments must apply to gas clouds orbiting ancient quasars. This assumption of cosmic consistency allows us to interpret distant light as meaningful information about places we can never visit. Future observations will undoubtedly refine our understanding of TON 618. The James Webb Space Telescope now peers deeper into space with unprecedented infrared sensitivity. Next-generation ground-based telescopes will capture even fainter signals with better resolution. Each technological advance reveals new details about distant objects, sometimes confirming previous estimates, sometimes forcing revisions. The act of measuring something like TON 680's attempt to comprehend scales that dwarf our everyday experience. We live on a planet orbiting an ordinary star in an unremarkable galaxy. Yet we've developed tools to study objects that contain the mass of tens of billions of stars. The contrast between our physical limitations and our intellectual reach creates a strange form of cosmic perspective, connecting us to phenomena that existed long before Earth formed. Every measurement of TON 618 adds another data point to our understanding of how black holes grow and evolve. The existence of such massive objects so early in cosmic history challenges models of black hole formation. How does something grow so large in the relatively short time since the Big Bang? The question connects individual measurements to broader puzzles about cosmic evolution, making each observation part of humanity's ongoing conversation with the universe. When we think about measuring something that exists beyond the reach of our senses, we're really talking about one of humanity's most remarkable achievements. The tools we use today can detect changes in light wavelengths that are smaller than a tiny fraction of a nanometer. To put that in perspective, that's like noticing the difference between 2 grains of sand from miles away. These detectors get cooled down to temperatures so close to absolute zero that they almost stop moving entirely. The reason for this extreme cold is simple. Heat creates noise, and noise interferes with the incredibly faint signals we're trying to capture. Meanwhile, telescopes scattered across different continents work together, synchronized like a perfectly timed orchestra, to create resolution that's sharper than any single mirror could ever achieve. The data from all this equipment gets fed into supercomputers that can process trillions of measurements, sifting through vast amounts of information to find the meaningful patterns hidden within. All of this incredible precision, all of this advanced technology, is focused on decoding signals that would appear to our naked eyes as nothing more than the faintest speck of light in the night sky. But here's something fascinating. It's not just our technology that makes these measurements possible. The universe itself cooperates with us in ways that seem almost designed for discovery. Light behaves exactly the same way everywhere, whether it's traveling through our atmosphere or crossing billions of years of empty space. Atoms emit and absorb specific wavelengths with perfect consistency, regardless of how far away they are or how long ago they released that light. This means that hydrogen in a distant quasar, one of the most energetic objects in the universe, leaves exactly the same spectral fingerprints as hydrogen sitting in a laboratory here on Earth. That reliability transforms the entire cosmos into something like a vast measuring instrument, where each photon becomes a tiny package of information, carrying a record of the conditions it experienced during its journey. The light from objects like TON 618, even though it's ancient beyond comprehension, still follows these same universal rules. That consistency is what allows us to bridge the enormous gap between here and there, between now and then. In many ways, the act of measuring such distant objects is really an act of time travel, that instead of moving ourselves through time, we're catching messages that time has delivered to us. Every photon that arrives at our detectors carries the imprint of a universe that no longer exists in that form. When we interpret these signals, we're essentially recreating a snapshot of the cosmos as it appeared more than 10 billion years ago. The black hole we're studying has almost certainly changed since then, but the data we receive preserves its ancient state, like a photograph frozen in light. Each measurement becomes a conversation with history, a dialogue that spans billions of years, conducted entirely in the language of electromagnetic radiation. Even though the black hole's true nature remains hidden behind its event horizon, the measurements we can make reveal its scale with astonishing clarity. When we say TON 618 has a mass equivalent to 66 billion suns, that's not just an abstract number. It represents a gravitational influence so immense that it could hold entire galaxies within its pull. The energy radiating from the superheated matter, spiraling into this black hole, is enough to outshine thousands of galaxies, like our own Milky Way. The fact that we can quantify such enormous phenomena from distances that stretch beyond imagination demonstrates how far scientific measurement has extended its reach. It shows us that even the most distant and powerful objects in the universe can be brought into focus through patience, precision, and methodical observation. But measuring the seemingly unmeasurable involves more than just collecting data. It's also about interpretation, about understanding what those numbers actually mean when we place them in context. The brightness of 218/618, for example, suggests that it's consuming matter at nearly the theoretical maximum rate, but probably not exceeding that limit. This balance tells us important things about how efficiently it's growing and what kind of environment exists in its host galaxy. The shape of the emission lines we detect reveals the orientation of the accretion disk relative to our position. Even tiny asymmetries in those spectral lines can tell us whether we're viewing the system face-on or from an angle. Every detail contributes to a larger understanding, each one forming a thread in the fabric of cosmic knowledge. There's something deeply human about this entire process. When faced with a universe so vast that its scale defies our everyday understanding, we somehow find ways to measure it using numbers small enough to fit on a page. We take light that has traveled for billions of years and translate it into data points and equations. We develop mathematical models for phenomena that no human will ever witness directly. Yet through this combination of curiosity and precision, we come to understand things that should theoretically be unknowable. TON 618 represents more than just an object of scientific study. It's a symbol of our ability to reach beyond the limits of direct observation, to measure, model, and make sense of what exists beyond sight. The uncertainties in our measurements don't diminish this achievement, they actually define it. Science thrives on the process of continuously refining what we know. Every estimate becomes a step toward greater clarity. Every revision an improvement on our previous understanding. The fact that we can discuss TON 618's mass with even approximate confidence is extraordinary in itself. The margin of error might seem vast by everyday standards, but the fundamental conclusion remains rock solid. This is genuinely one of the largest black holes ever discovered, a structure whose very existence challenges our models of how cosmic evolution works. As our instruments continue to improve, we'll likely discover more objects like this one, perhaps some that are even larger. Each new discovery adds another point on the map of cosmic possibilities, another dataset for comparison and analysis. With every fresh measurement, our models of galaxy formation and black hole growth become more refined and accurate. This process never truly ends because the universe consistently proves to be deeper and more complex than our current understanding. The goal of measuring the unmeasurable isn't about reaching some final endpoint of knowledge, but about continuously extending the boundary of what can be known and understood. In this sense, every photon arriving from TON 618 acts as a teacher. Each one has traveled across the expanding fabric of space-time, carrying information about gravity, temperature, motion, and the fundamental physics of extreme environments. By capturing those photons, by measuring their energy and direction, we participate in the ongoing act of decoding the universe itself. It's a slow, meticulous conversation, conducted in complete silence, yet somehow filled with profound meaning. Even though the object we're studying remains invisible to us, the data it provides shines brightly enough to illuminate the very edges of what science can grasp and comprehend. The numbers we derive from these observations might never feel intuitive on a human scale, but they form a bridge between abstract thought and cosmic reality, between our curiosity and the vast unknown. This unseeable giant remains our most distant mirror, reflecting not just the incredible power of gravity and space-time, but the fundamental human drive to understand what lies beyond every horizon we can possibly measure. The vastness of space stretches beyond our imagination, filled with countless islands of light we call galaxies. Each one contains billions of stars, swirling together in patterns that seem almost too perfect to be random. Some galaxies spiral gracefully, their arms reaching out like cosmic pinwheels. Others appear as smooth, oval shapes, glowing softly against the darkness. Then there are the irregular ones, twisted and pulled into strange forms by ancient collisions. What's truly remarkable is that every single one of these massive structures, containing more stars than we could ever count, is held together by something we cannot see. Deep at the heart of nearly every galaxy lies a supermassive black hole. These cosmic monsters are so dense that not even light can escape their grip, yet they're responsible for organizing everything around them. For decades, astronomers believed black holes were rare, cosmic accidents. They thought maybe a few unlucky stars collapsed in just the right way to create these mysterious objects. But as our telescopes got better, a different picture emerged. Scientists started noticing that stars near the centers of galaxies were moving far too fast. Something invisible was pulling them along at incredible speeds. Gas clouds were whipping around empty space as if chased by a massive gravitational field. The evidence kept piling up. Light from distant stars would bend and curve as it passed through what appeared to be empty space. The only explanation that made sense was that something incredibly massive was hiding there, something so dense it warped space itself. Eventually, the conclusion became undeniable. Almost every large galaxy in the universe has a supermassive black hole sitting right at its center. Some of these black holes are what we call active. They're feeding constantly, pulling in gas and dust and heating it until it glows brighter than entire galaxies. We call these quasars, and they can be seen from billions of light years away. Others have gone quiet, sitting dormant like sleeping giants, barely detectable except for their gravitational influence. It's tempting to think of black holes as purely destructive forces, cosmic vacuum cleaners that consume everything in their path, but that's not really how they work. In the grand scheme of things, they're more like cosmic architects. Their gravity pulls gas and dust toward galactic centers, creating dense regions where new stars can form more easily. They stabilize the orbits of nearby stars, keeping them from drifting away into empty space. Perhaps most importantly, they act as regulators. When a black hole feeds, it doesn't do so quietly. The process releases enormous amounts of energy that heats up surrounding gas and can even blow it away from the galaxy entirely. This might seem wasteful, but it actually serves a crucial purpose. Without this regulation, galaxies would form stars too quickly, burning through their fuel and dying young. This creates what scientists call a feedback loop. The black hole and its galaxy grow together, each one influencing the other in a delicate cosmic dance that lasts billions of years. If the galaxy gets too active in forming stars, the black hole responds by heating up the available gas, slowing things down. If star formation drops too low, the black hole becomes quieter, allowing more gas to cool and condense into new stars. This relationship is so consistent that astronomers have discovered a remarkable pattern. The size of a galaxy's central bulge, that dense core of older stars, is directly related to the mass of its central black hole. Bigger bulge means bigger black hole, smaller bulge means smaller black hole. This correlation holds true across millions of galaxies, suggesting that their growth is intimately connected. Our own Milky Way follows this pattern perfectly. At our galaxy's heart sits Sagittarius A star, a supermassive black hole about 4 million times more massive than our Sun. It's relatively quiet these days, but the region around it tells a different story. There are gas clouds heated to extreme temperatures, radio waves from ancient jets of material, and clusters of stars that probably formed when the black hole was much more active. All of this evidence suggests that billions of years ago, our galaxy's central black hole was feeding much more actively. It might have even shone as brightly as a quasar, visible from across the universe. Looking at active galaxies today is like looking back at what the Milky Way might have been in its youth, wild and energetic and still growing rapidly. The influence of these central black holes extends far beyond their immediate neighborhoods. Even stars that are many light years away feel their gravitational pull. The shape of spiral arms, the stability of gas clouds, the overall structure of the galaxy, all of these depend at least partly on that invisible presence at the center. Without such a massive anchor, galaxies might simply disperse over time. Their stars would drift apart into the void, leaving behind only scattered points of light with no organization or structure. The black hole acts as a gravitational foundation, giving the entire system something to organize around. This might seem contradictory at first. How can something that consumes light and matter also be responsible for building structure? The answer lies in that feedback process we mentioned earlier. It's not just about destruction, it's about balance and timing. A black hole that feeds too aggressively will blow away the very material needed to form new stars. One that's too quiet won't provide enough regulation to prevent the galaxy from burning out too quickly. The most massive black holes, like the monster known as Taurn A's 218, represent this process taken to its absolute extreme. This particular black hole is so massive that it defies easy comprehension. Its gravitational influence extends across vast regions of its host galaxy, shaping the orbits of billions of stars and controlling the flow of matter across interstellar distances. Even dwarf galaxies, the smallest galactic systems we know of, follow this same pattern. Recent studies have found evidence of black holes at their centers too, smaller than their giant cousins, but still proportional to their host galaxy's mass. From the tiniest collections of stars to the largest galaxy clusters, this relationship holds true. It's as if the universe has a fundamental rule about building structure around these dense cores. Think of it like a conductor leading an orchestra. The conductor doesn't play any of the instruments, but without that guiding presence, the musicians would quickly fall out of sync. The result would be chaos instead of harmony. Black holes serve a similar function in their galaxies, setting the rhythm and keeping billions of stars moving together in organized patterns. Of course, all of this happens on timescales that dwarf human experience. The feedback cycles that shape galaxies unfold over millions or billions of years. Stars near the galactic center might take entire geological ages just to complete one orbit. The energy released by a feeding black hole can influence star formation for cosmic eons. When we look at galaxies through our telescopes, we're seeing the results of this slow, patient process of construction. Each spiral arm, each glowing region of star formation, each stable orbit represents the cumulative effect of billions of years of gravitational choreography. The invisible conductors at galactic centers have been working tirelessly since the universe was young, building the cosmic architecture that surrounds us today. It's a humbling thought that something we cannot see directly has such profound influence over the largest structures in the universe. These silent architects work behind curtains of gas and dust, shaping the cosmic landscape through nothing but gravity and energy. They remind us that the most important forces in the universe are often the ones we cannot observe directly, known only through their effects on everything around them. When we peer into the depths of space, we're essentially time travelers, witnessing moments frozen from billions of years ago. The light reaching our telescopes today carries stories from when the universe was fundamentally different, younger, more chaotic. Think about it. Every photon has been journeying through the void for eons, carrying with it a snapshot of cosmic history that we can barely begin to comprehend. The relationship between black holes and their host galaxies tells a fascinating story of cosmic evolution. In the early universe, things were far more violent, more active than they are today. Back then, supermassive black holes were feeding voraciously, consuming vast amounts of material and shining as brilliant quasars across the cosmos. These weren't the quiet, dormant giants we often imagine today, but rather cosmic beacons that could outshine entire galaxies. Scientists have discovered something remarkable when they study galaxies at different distances, which means looking at different periods in cosmic history. The pattern is clear. Younger galaxies tend to host much more active black holes, while older, more mature galaxies, it's almost like watching a civilization grow up, moving from the wild energy of youth to the steady wisdom of age. This feeding frenzy wasn't random or chaotic, despite appearances. There was a method to the madness, a cosmic choreography playing out over billions of years. During these early epochs, gravity and gas were locked in constant competition, with black holes growing rapidly as they devoured everything within reach. The energy released during this process was tremendous, creating some of the brightest objects ever observed in the universe. But here's where things get philosophically interesting. Even when a black hole stops actively feeding, when it becomes what we might call dormant, its work as an architect doesn't end. The gravitational influence continues, invisible but profound, keeping stars in stable orbits for billions of years. It's like a master builder who constructs a foundation so solid that the structure continues to thrive long after the construction ends. The universe operates on a scale that challenges our everyday understanding of cause and effect. When galaxies eventually merge, which happens more often than you might think, their central black holes merge as well. These cosmic collisions send ripples through the very fabric of spacetime itself, gravitational waves that travel at the speed of light across the universe. Future space-based observatories will be able to detect these waves, essentially allowing us to listen to the heartbeat of cosmic architecture. The influence of these massive objects extends far beyond their immediate surroundings. The jets and winds they produce during their active phases inject enormous amounts of energy into the space between galaxies. This isn't just empty void, but rather a complex medium filled with gas and particles that future galaxies will use as building material. In this way, the actions of one supermassive black hole can influence the formation of galaxies millions of light-years away. Consider the cosmic web, that vast network of filaments and voids that defines the large-scale structure of everything we can observe. Black holes play a crucial role in shaping this web, depositing material and energy across distances that boggle the mind. Their jets can stretch for millions of light years, creating channels and structures that persist long after the black hole itself has quieted down. There's something almost poetic about the fact that all of this complexity, all of this cosmic architecture, emerges from the simplest possible rule: gravity pulls. There's no conscious design behind it, no grand plan or intention. Yet the results are breathtakingly intricate. Black holes represent endpoints of gravitational collapse, but that same collapse drives creation everywhere else in the universe. Without these invisible architects, the universe would be fundamentally different. Flatter, less structured, arguably less interesting. The contrast they create between regions of extreme density and relative emptiness gives the cosmos its distinctive character. They introduce dynamics that drive star formation, galaxy evolution, and the complex dance of matter and energy that we observe today. When astronomers study the most extreme examples of these objects, they're not just learning about individual black holes, but about the entire process of cosmic construction. The most massive and energetic cases represent extreme versions of processes that happen everywhere, on every scale. By understanding how the giants formed and evolved, we gain insights into how our own galaxy, our own solar system, came to exist. Every new observation adds another piece to an enormous puzzle, revealing how gravity and energy have balanced each other over cosmic time. It's a humbling reminder that even the most remote and violent corners of the universe are intimately connected to our own origins, our own existence. The term quiet architects really captures something essential about these objects. They don't announce their work with fanfare or obvious signs. Their influence is largely invisible, indirect, and slow, unfolding over timescales that dwarf human history. Yet without them, the night sky we know simply wouldn't exist. They provide galaxies with their centers, their structural stability, and often their most spectacular displays of energy. Even when they fade from our view, becoming too dim to detect directly, their gravitational signatures remain, continuing to shape the motion of countless stars for billions of years into the future. In this way, they serve as both creators and witnesses, building the framework of the universe while remaining hidden within the very structures they helped create. Our understanding of these cosmic architects continues to evolve as new technologies allow us to peer deeper into space and further back in time. Supercomputer simulations reveal intricate feedback cycles where jets and radiation sculpt vast regions of gas, where the precise timing of events determines whether a galaxy thrives or fades. The more we model these systems, the clearer it becomes that the line between destruction and creation is remarkably thin. The universe seems to thrive precisely in this tension between opposing forces. Matter falling into black holes releases energy that prevents other matter from falling in, creating a delicate balance that has persisted for billions of years. This cosmic equilibrium has allowed stars to form, planets to coalesce, and eventually, life to emerge in at least one corner of the universe that we know of. Looking toward the future, we can imagine discovering even larger black holes, even more massive galaxies, even clearer patterns in the cosmic web. But the fundamental principle will likely remain unchanged. Every structure we observe, from the smallest asteroid to the largest galaxy cluster, traces its ancestry back to the same basic process: gravity gathering matter around invisible centers. The galaxies we see today, mature and relatively calm, owe their current form to those early active periods when supermassive black holes dominated their centers. Though this ancient work is now invisible, its results surround us everywhere we look. In the elegant spirals of distant galaxies, in the careful balance of forces that allows planets like Earth to exist, and in the quiet persistence of gravity, organizing everything from individual atoms to vast clusters of galaxies. When we step outside on a clear night and look up at the stars, we're seeing the architecture left behind by these processes. We're observing the product of forces that built and balanced the universe long before our solar system even existed. And at the heart of it all, silent and largely unseen, the black holes remain, continuing their work as the quiet architects of cosmic structure, the steady anchors of a universe that organized itself through nothing more complex than the simple pull of gravity. When we point our telescopes at distant objects in space, we're doing something extraordinary. We're traveling through time. The light from these faraway places doesn't reach us instantly. It takes time to cross the vast emptiness between stars and galaxies. Consider this. Every single photon that hits our instruments today began its journey long ago. Some started traveling before humans existed. Others left their source before Earth itself had formed. The farther something is from us, the older its light becomes by the time we see it. This means the night sky isn't showing us what's happening now. It's a collection of different moments, scattered across billions of years. Each point of light represents a different slice of history. The star you see tonight might have already died, but its light is still making the journey to your eyes. Out there in the cosmos, there's an object called T-O-N-A. Out there in the cosmos, study it, they're looking at light that's over 10 billion years old. That light started its journey when the universe was just a quarter of its current age. Back then, everything was different. The universe was smaller, hotter, more chaotic. Galaxies were closer together, constantly bumping into each other. These collisions triggered massive bursts of star formation. New suns ignited everywhere, burning bright and blue in the cosmic darkness. During that ancient era, the space between galaxies wasn't as empty as it is today. There was more gas, more dust, more activity. The temperature of empty space itself was higher than what we measure now. The afterglow from the Big Bang still warmed everything with a gentle heat that has long since faded away. TON 618 was born in this turbulent time. It's what we call a quasar, powered by a black hole so massive it defies easy understanding. This black hole grew to incredible size by feeding on the abundant material around it. Gas and stars spiraled inward, heating up and glowing brilliantly before disappearing forever. The light we receive from TON 618 has been stretched during its long journey. As the universe expanded, the wavelengths of that ancient light got longer and longer. This stretching tells us exactly how far back in time we're looking. It's like a cosmic timestamp, marking when that light first began its journey toward us. What's fascinating is that this stretching happens to all light traveling through expanding space. The effect is subtle for nearby objects, but becomes dramatic for the most distant ones. By measuring how much the light has been stretched, astronomers can calculate both distance and time with remarkable precision. Think about what this means for our understanding of existence itself. We're not just observers looking out into space. We're time travelers, peering into epochs that no longer exist. The universe we see through our telescopes is a museum of cosmic history, with each object representing a different era. The photons from TON 618 have crossed an unimaginable amount of space and time to reach us. They've passed through clouds of gas, around massive galaxy clusters, through regions of nearly perfect vacuum. Some got absorbed and re-emitted along the way. Others were bent by gravity or scattered by dust. But enough survived the journey to tell their story. Each photon carries information about conditions that existed when the universe was young. The energy patterns, the chemical signatures, the brightness variations. All of these details help scientists reconstruct what that ancient cosmos was like. It's detective work on the grandest possible scale. This process of looking backward through time isn't unique to TON 618. Every astronomical observation works the same way. When you look at the moon, you're seeing it as it was about a second ago. The sun appears as it was 8 minutes in the past. Nearby stars show us their light from years or decades ago, but with objects like TON 618, we push this time travel to its limits. We're seeing the universe when it was still figuring out its basic structure. Galaxies were forming from primordial gas clouds. The first generations of stars were creating heavy elements that didn't exist before. The cosmic web of matter was just beginning to take shape. The existence of such a massive black hole, so early in cosmic history, surprised many scientists. Current theories suggest it should have taken much longer for something so large to form. TON 618 forces us to reconsider how quickly gravity can assemble matter in the young universe. This challenges our models of cosmic evolution. Perhaps black holes grew faster than we thought. Maybe there were different processes at work in the early universe that we don't fully understand yet. Each new observation like this helps refine our picture of how everything began. What's remarkable about this cosmic archaeology is that we don't need to travel anywhere to do it. We simply wait for the light to come to us. Our telescopes act as time machines, collecting ancient photons that have been journeying across space for billions of years. The James Webb Space Telescope has pushed this even further, capturing light from galaxies that formed when the universe was just a few 100 million years old. These observations show us the cosmic dawn, when the first stars began to shine and clear away the darkness. From the perspective of a photon, though, the journey is instantaneous. Light doesn't experience time the way we do. For those particles of light, the trip from TON 618 to Earth happens in no time at all. But from our viewpoint, anchored in our local frame of reference, that same journey spans most of cosmic history. This reveals something profound about the nature of time itself. It's not universal or constant. It depends on your motion, your gravity, your perspective. Einstein showed us that time and space are woven together into a single fabric that can bend and stretch. When we study distant objects like TON 618, we're seeing this principle in action. We're witnessing how the universe looked when it was fundamentally different from today. The galaxies were more active, stars formed more rapidly, and massive black holes dominated the cosmic landscape. This connects us to the deep past in a very real way. The light touching our instruments right now was present when Earth was just forming. It has witnessed the entire history of our solar system from a distance, carrying that ancient energy across the expanding universe until this moment. In studying these distant beacons, we learned that the universe has always been a place of constant change. Nothing stays the same. Stars are born, live their lives and die. Galaxies merge and evolve. Even space itself continues to expand and cool. TON 618 represents a snapshot from when this cosmic story was still in its opening chapters, a time when the universe was more energetic, more chaotic, but also more creative. The light from that era serves as a bridge between then and now, connecting ancient history with our present moment of discovery. The journey that light takes from distant quasars to reach us tells a story far more complex than we might imagine. When photons leave objects like the supermassive black hole TON 618, they don't simply race through empty space in a straight line. Instead, they weave through what astronomers call the cosmic web, a vast network of dark matter filaments and gas that connects galaxies across the universe like an enormous 3D matter, leave their mark on every beam of light that passes through them. The photons get slightly absorbed, scattered, and altered in ways so subtle that only our most sensitive instruments can detect them. It's remarkable, really, how the universe writes its autobiography in these tiny changes to starlight. Scientists can read these modifications like fingerprints, mapping out structures that would otherwise remain completely hidden from view. What emerges from this detective work is nothing short of extraordinary. Each photon becomes a messenger carrying multiple stories simultaneously. One story tells us about the black hole that originally emitted the light, its mass, its spin, the furious activity around its event horizon. But another story reveals everything that light encountered on its billions of years long journey through space. The density of hydrogen clouds, the temperature of gas floating between galaxies, even the invisible influence of dark matter stretching and bending the fabric of space-time itself. This dual nature of cosmic light creates something profound for our understanding. We're not just looking at distant objects, we're literally observing the universe as it used to be. TON 618 appears to us as it existed over 10 billion years ago, when the cosmos was younger, wilder, more chaotic than today. By comparing quasars at different distances, astronomers can watch the universe evolve in slow motion, seeing how star formation rates changed over time, how galaxies grew and merged, how the space between them gradually cooled and thinned. It's like having access to a cosmic photo album, where each image captures the universe at a different stage of its development. The nearest quasars show us relatively recent cosmic history, while the most distant ones, like TON 618, take us back toward the dawn of time itself. This ability to peer backward through history reveals something both humbling and beautiful about the temporary nature of everything we observe. The brilliant light streaming from TON 618 won't last forever. Eventually, the supermassive black hole will exhaust its fuel, the accretion disk will fade, and the quasar will go dark. The galaxy itself will settle into a quieter existence, its most dramatic chapter closed. Even the black hole's Hawking radiation will eventually dissipate over timescales so vast they dwarf the current age of the universe. Yet this impermanence doesn't diminish the significance of what we're witnessing, it amplifies it. Everything we know about this distant giant comes purely from electromagnetic radiation, waves of energy that have crossed unimaginable distances to reach us. No physical samples, no debris, no material evidence beyond photons themselves. The fact that these massless particles can carry such detailed information across billions of light years speaks to something almost miraculous about the fundamental language of physics. There's something deeply philosophical about this relationship between light and knowledge. These ancient photons streaming toward us carry memories encoded in their wavelengths, their polarization, their spectral signatures. They preserve information about events that occurred when the universe was a completely different place. In a very real sense, every astronomical observation becomes an act of archaeology, digging through layers of cosmic time preserved in starlight. The elements that make up our planet, our bodies, our entire world, were forged during the same epochs when quasars like TON 618 blazed across the early universe. The heavy elements created in massive stars during those ancient times eventually found their way into later generations of planets and life forms. We are, quite literally, made from the same cosmic processes that we observe when we study distant quasars. This creates an almost mystical connection between observer and observed. Looking at TON 618 becomes a form of cosmic genealogy, tracing our origins back through billions of years of stellar evolution and galactic development. The light reaching our telescopes today began its journey long before Earth even existed, yet it connects us directly to the conditions that would eventually lead to our solar system's formation. Modern instruments continue pushing deeper into space and further back in time, revealing quasars even more ancient than TON 618. Each new discovery takes us closer to the very beginning of cosmic history, when the first stars ignited, when the first black holes formed, when the universe transitioned from darkness to light. These observations don't rely on speculation or theory alone. They provide direct evidence of conditions in the primordial cosmos. The photons streaming past us every second carry this vast archive of cosmic memory, waiting for us to develop the tools and techniques needed to decode their messages. Every point of light in the night sky represents a portal into history, a direct connection to events that shaped the universe we inhabit today. The continuing journey of exploration through astronomical observation reminds us that we exist as part of an ongoing story that stretches across space and time on scales that challenge our very ability to comprehend them. The cosmic web stretches across the universe like an invisible highway system, connecting everything through vast filaments of dark matter and gas. These filaments act as rivers, channeling material from empty regions toward gravitational wells where galaxies form. Where multiple filaments intersect, you get the densest regions of all, perfect nurseries for massive galaxies and their central black holes. Dark matter makes up about 85% of all matter in the universe, yet we can't see it directly. It reveals itself only through its gravitational effects, bending light and holding galaxies together. Without dark matter providing this invisible scaffolding, ordinary matter would never have had enough time to clump into stars and galaxies. The universe would have remained smooth and featureless, expanding too quickly for structure to take hold. In the early universe, roughly 3 billion years after the Big Bang, conditions were dramatically different from today. The space between galaxies was warmer, denser, filled with gas that flowed like cosmic rivers. The universe was only about 1/5 of its current age, still learning how to balance the forces that shape it. Temperature differences were more extreme, gravitational gradients steeper, and the pace of change much faster. This was an era of what physicists call super Eddington accretion. Black holes were feeding beyond what theory suggested should be possible. The Eddington limit describes how fast a black hole can consume matter before its own radiation pressure pushes new material away. But in the early universe, matter sometimes flowed inward so rapidly that radiation couldn't escape quickly enough to halt the process. The first heavy elements were just beginning to appear, forged in the cores of massive stars and scattered by supernova explosions. Carbon, oxygen, silicon, iron, these new ingredients changed everything. They enabled more complex chemistry, allowed planets to form eventually, and helped black holes grow more efficiently. Before this cosmic enrichment, the universe contained only hydrogen and helium, limiting what kinds of structures could emerge. Direct collapse offers one explanation for how supermassive black holes grew so large so quickly. Instead of forming from stellar remnants, massive clouds of primordial gas collapsed straight into black holes without ever becoming stars. These seed black holes could start with masses hundreds of thousands of times greater than our Sun, giving them a significant head start in the cosmic feeding race. Galaxy mergers were incredibly common in the early universe, driven by the smaller distances between young galaxies and their stronger gravitational interactions. When galaxies collide, their stars rarely hit each other directly. The spaces between them are simply too vast, but their gas and dust mix violently, creating shock waves that trigger intense bursts of star formation. The cosmic microwave background radiation, the afterglow of the Big Bang, was much hotter in those early times. As the universe expanded and cooled, this background temperature dropped enough for the first galaxies to form clearly, but the space between them remained warmer and thicker with gas than it is today, creating a very different environment for cosmic evolution. Primordial gas consisted almost entirely of hydrogen and helium, the simplest elements. These light elements behaved differently from the enriched gas we see in modern galaxies. Without heavier elements to help cool gas clouds, the process of star formation was less efficient. Stars had to be much more massive to form at all, leading to shorter lifespans and more dramatic deaths. Gravitational waves from merging black holes rippled through spacetime during these cosmic collisions. When two galaxies merged, their central black holes would spiral toward each other over millions of years, eventually combining in events so powerful they distorted space itself. These waves traveled at the speed of light, carrying energy away from the merger and allowing the black holes to finally unite. Quasars served as the first great lighthouses after the cosmic dark ages. Before stars formed, the universe was filled with neutral hydrogen that absorbed light, making space opaque like a thick fog. The radiation from early stars and quasars gradually stripped electrons from hydrogen atoms, clearing this fog and making the universe transparent for the first time since the Big Bang. The balance between gravity pulling inward and radiation pressure pushing outward determined how quickly black holes could grow. When this balance tipped toward gravity, as it often did in the dense early universe, black holes entered periods of rapid growth. Their accretion disks became thicker, denser, and more chaotic than anything we observe in modern quasars. Star formation rates in the early universe were extraordinary compared to today. Young galaxies converted gas into stars at rates tens or hundreds of times faster than modern galaxies. This stellar baby boom was fueled by the abundant gas supplies and frequent galaxy interactions that characterized the cosmic youth. The temperature of space itself tells us about cosmic history. Today, the universe averages about 3 degrees above absolute zero. But when the light from distant quasars began its journey, the cosmic background temperature was significantly higher, affecting how gas behaved and how structures formed. Each generation of stars enriched the universe with heavier elements, making the next generation more complex. This process built upward, layer by layer, from simple hydrogen and helium to the rich diversity of elements we find today. The universe was literally learning chemistry, one stellar explosion at a time. Cosmic filaments channel matter across billions of light years, connecting galaxy clusters through an intricate web of dark matter and gas. These structures formed early in cosmic history and continue to funnel material toward the densest regions, where it feeds both star formation and black hole growth. The opacity of the early universe meant that light couldn't travel far before being absorbed. This cosmic fog began lifting as the first stars ionized surrounding hydrogen, but the process took hundreds of millions of years to complete. During this transition, the universe gradually transformed from shadow into light. Radiation pressure from accreting black holes created a complex feedback loop with their host galaxies. Sometimes this radiation heated nearby gas so much that it prevented new stars from forming. Other times, it compressed gas clouds further out, actually triggering star formation. This delicate interplay helped regulate the pace of cosmic evolution. The cosmic web wasn't just a passive structure, it was actively bright with energy. Gas flowing along filaments glowed with radiation, creating a luminous network that connected galaxies across vast distances. This ancient light has since faded as the universe expanded and cooled, but its effects shaped everything we see today. When light first escaped from this ancient giant, the cosmos itself was in the midst of profound change. Star formation had reached its peak across the universe, and from that moment forward, everything began to slow down. The easily available fuel that powered cosmic creation was running low, galaxy by galaxy. Think about it this way. The universe was like a young person with an enormous appetite, consuming everything in sight. But as it matured, that hunger naturally subsided. The galaxies that formed later became quieter places, their stars burned more steadily, their central black holes grew less violent. This massive object known as TON 618 represents something like a fossil from those wild early days. It's a preserved record of just how voracious the universe once was. During its most active period, this black hole devoured matter equivalent to thousands of Earth masses every single year. The energy it released during those feeding frenzies exceeded what countless entire galaxies produce combined. That's not just impressive from a distance, it actually reshaped the fabric of space around it. The radiation pushed gas clouds outward, across millions of light years, heated up entire regions of space, and even prevented smaller nearby galaxies from growing properly. Back then, the universe was much denser than it is today. Galaxies sat closer together, which meant these massive influences overlapped constantly. You had this intricate web of interactions, where one feeding black hole could affect dozens of others across vast distances. The radiation from TON 618 scattered and mixed into what we now call the cosmic microwave background, that faint glow that fills all of space today. Hidden somewhere in that gentle warmth are the remnants of ancient fury, blended together with light from countless other giants that once burned, just as fiercely. Understanding this early period requires more than just pointing telescopes at distant objects. Astronomers run complex simulations on supercomputers, recreating the conditions of the young universe step by step. These digital recreations consistently show that early quasars, like TON 618, played crucial roles in shaping everything that came after. They heated vast regions of space, ionized the gas between galaxies, and essentially set the tempo for future star formation. Without these early giants, the universe we see today would look completely different. The very existence of TON 618 proves that the extreme conditions needed for such growth weren't rare accidents. They were common enough to leave permanent marks on cosmic evolution. It's tempting to think of that young universe as chaotic or violent, but there was actually a strange efficiency to it all. Every burst of energy, every collision between galaxies, every feeding episode contributed to a delicate balance that allowed the cosmos to eventually settle into maturity. The energy released by quasars wasn't wasted, it spread outward systematically, enriching and shaping the regions around them. Over billions of years, that energy cooled down, galaxies found stable orbits, and star formation became more predictable. But the memory of that early hunger remains encoded in the large-scale structure of space itself. Even today, we can trace this legacy in multiple ways. The heavy elements we detect in intergalactic gas, things like oxygen, carbon, and iron, were forged inside those early massive stars and scattered by their explosive deaths. The supermassive black holes sitting at the centers of modern galaxies are direct descendants of those early giants. The background radiation we pick up with radio telescopes still carries the thermal imprint of their heating effects. Every observation points back to the same fundamental period. When the universe was young, incredibly hot, and driven by an almost insatiable appetite for growth and transformation. But this isn't just a story about scale and size, it's really a story about transformation itself. The matter that once swirled in the accretion disk around Ton 618 has since become part of entirely new galaxies, new stars and new planetary systems. The hydrogen atoms that fell into this black hole billions of years ago may have originally drifted in the vast spaces between galaxies. And the atoms that managed to escape the gravitational pull likely went on to form other cosmic structures entirely. Even destruction feeds creation, given enough time. As the universe continued to age, the expansion of space stretched everything farther apart and cooled the overall temperature. Galaxies drifted away from each other, collisions became less frequent, and that great cosmic hunger began to quiet down naturally. Ton 618's feeding phase, once a blazing beacon visible across the cosmos, probably subsided long ago. The fuel supply ran out, the accretion process slowed to a crawl, and the brilliant glow faded into darkness. Yet the black hole itself remains unchanged, its enormous mass still there, its gravity still holding its host galaxy together. What was once the violent heart of a cosmic storm has become something like a monument to what the universe used to be. It's proof that even apparent chaos can lead to order when given sufficient time to work itself out. The young universe was hungry because it was growing, learning how to organize itself into increasingly complex structures. It consumed raw material to create new forms, destroyed simple arrangements to build more sophisticated ones, and radiated energy to maintain overall balance. Through this process, the first great cosmic structures emerged from primordial simplicity. Everything we observe today, from the faint light of the most distant galaxies to the atoms that make up our own bodies, found its place through this ongoing transformation of matter and energy. Ton 618, frozen in light from that ancient era, serves as a window into that primordial hunger. Not just the hunger of gravity pulling on matter, but the hunger of the universe itself to become more complex, more organized, and more alive with possibility. It reminds us that the relative calm we observe in the modern cosmos was born from incredible intensity. The peaceful state of today's universe rests on foundations laid during an age of fire, constant motion, and seemingly insatiable growth. And somewhere in the depth of that ancient light, still traveling toward us across impossible distances, the echoes of that cosmic hunger continue their journey, carrying the story of a universe that once consumed itself in order to learn how to truly shine. The cosmos stretches beyond anything our minds can truly grasp. When we peer into the night sky, we're looking at a fraction of something much larger. The observable universe, that sphere of space from which light has had time to reach us, represents just a tiny bubble in an ocean we'll never fully see. Light travels fast, but not infinitely fast. This simple fact creates one of the most profound boundaries in all of science. There's a horizon beyond which no signal can ever arrive, no matter how long we wait. Space itself expands faster than light can cross it, in some regions, creating a permanent veil over vast portions of reality. Think about what this means. There are galaxies, stars, perhaps entire civilizations that exist beyond our cosmic horizon. They're real, they're out there, but they might as well be in another universe entirely. The finite speed of light becomes a cosmic prison, keeping us forever isolated from the full truth of what surrounds us. Near this boundary, we find objects that challenge everything we think we know. Supermassive black holes like Ton 618 sit at the edge of our vision, their light arriving from when the universe was young. These monsters contain the mass of tens of billions of suns, yet they formed when space was supposedly too young for such giants to exist. The mathematics of black hole growth tells a clear story. A black hole needs time to consume matter, to merge with other holes, to reach enormous sizes. But TON 618 breaks this timeline. It exists when our models say it shouldn't, like finding a fully grown tree in soil that was planted yesterday. This creates a fascinating puzzle that sits right at the limits of our understanding. Either black holes can grow much faster than we thought, or the early universe operated under different rules than we imagine. Perhaps there were shortcuts to massive growth that we haven't discovered yet. Perhaps the very first black holes formed through processes we've never observed. The beauty of science lies in these moments of confusion. When our best theories encounter something they can't explain, we know we're approaching the frontier. Every major breakthrough in physics has come from exactly this kind of contradiction, where reality refuses to fit inside our carefully constructed boxes. Consider how our view of the cosmos has evolved. There was a time when people thought the Milky Way was the entire universe. Then we discovered other galaxies. Then we found that space itself is expanding. Each revelation pushed the boundary of knowledge further out, revealing new mysteries behind the old ones. Black holes represent one of the strangest predictions that physics ever made. Einstein's equations described them decades before anyone found one. They showed that matter could collapse so completely that it would tear a hole in the fabric of space and time itself. Even Einstein found this idea disturbing, hoping that nature would find some way to prevent such extreme objects from forming. But nature, as we've learned, is far more creative than our intuitions suggest. Black holes don't just exist, they thrive. They anchor galaxies, they merge and grow. They warp space so severely that time itself slows down near their edges. The largest ones, like TON 618, create gravitational fields so intense that they can be detected from billions of light years away. When we observe these distant giants, we're not just looking at objects in space, we're looking backwards through time itself. The light from TON 618 began its journey when the universe was less than a tenth of its current age. We're seeing this black hole as it was in the cosmic dawn, when the first galaxies were still forming from primordial gas clouds. This time machine effect reveals something profound about the nature of observation itself. We can never see the universe as it is right now. We can only see how it was, layer upon layer of the past, stacked like pages in an ancient book. The further we look, the deeper into history we peer, until we reach the very limits of what light can show us. Near those limits, our most fundamental theories begin to strain. General relativity describes how massive objects bend space and time, creating the phenomenon we call gravity. Quantum mechanics governs the behavior of matter and energy at the smallest scales. Both theories work perfectly within their own domains, but they tell different stories about what happens inside black holes. Relativity predicts that matter falling into a black hole will collapse to infinite density, creating what physicists call a singularity. It's a point where the normal rules of space and time break down completely. Quantum theory, however, rebels against infinities. It suggests that something must intervene to prevent such extreme collapse, though we don't know what that something might be. This conflict between our two most successful theories reveals the edge of human knowledge in its purest form. We have equations that describe the universe with incredible precision, yet they contradict each other at exactly the point where we need them most. Inside every black hole lies a question that our current physics cannot answer. The search for a unified theory, one that combines gravity with quantum mechanics, represents one of the greatest challenges in modern science. Such a theory would need to describe both the vast and the tiny in a single, consistent framework. It would need to explain how space and time emerge, how matter behaves under extreme conditions, and what really happens at the center of objects like TON 618. These aren't just abstract puzzles for theoretical physicists to ponder. They're fundamental questions about the nature of reality itself. The answers might reveal whether our universe is unique or part of a vast multiverse. They might tell us how time began and whether space has limits. They might even illuminate the deepest question of all: why anything exists rather than nothing. Every time we build better telescopes, we push the cosmic frontier a little further out. Radio astronomy revealed galaxies invisible to optical instruments. Space telescopes escaped the blurring effects of our atmosphere. Now, the most advanced observatories can detect light from stars that formed just a few 100 million years after the Big Bang itself. Yet, the more we see, the more mysterious the universe becomes. Each answer generates new questions. Each discovery reveals new puzzles. The cosmic horizon retreats before us like a mirage, always promising more wonders, just beyond our reach. In this endless pursuit of understanding, objects like TON 618 serve as both destination and guide, marking the current limits of what we can know while pointing toward truths still waiting to be discovered. The study of distant objects like massive black holes tests something deeper than our instruments. It challenges the very foundations of how we understand reality. When we peer into the cosmos, we quickly encounter the edges of what can ever be known. Light has been traveling since the Big Bang, creating a kind of cosmic horizon beyond which nothing can be seen. This isn't a physical wall somewhere out in space. It's a boundary created by time itself. Think about it for a moment. Most of the universe remains permanently hidden from us. Entire galaxies exist beyond that horizon. Their light will never make the journey to reach Earth. The universe may stretch on infinitely, filled with wonders we can never witness. There's something both humbling and strangely reassuring about this limitation. It means the unknown will always be larger than the known. Astronomers work within these constraints by studying what they can observe in extraordinary detail. They build models, test predictions, refine their understanding bit by bit. When their calculations match what they see through telescopes, confidence grows that the unseen parts of the universe follow the same physical laws. When the data doesn't fit, that's often where the most important discoveries begin. Objects like the supermassive black hole, known as 2618, push these tests to their absolute limits. Its brightness defies easy explanation. Its mass stretches the boundaries of what current models can accommodate. Its age raises questions about how quickly such enormous objects could have formed in the early universe. These extreme cases keep science honest. They remind us that our theories are temporary scaffolding around a truth too vast to fully contain. At the edges of human knowledge, humility becomes an essential scientific tool. The willingness to admit uncertainty, to revise or even abandon long-held ideas. This flexibility allows discovery to continue moving forward. Every time researchers point their most powerful instrument towards something as distant as TA18, they're doing more than confirming what they expect to find. They're also searching for that moment when expectation breaks, when the data no longer matches the theory. The technical challenges of observing such distant objects push our methods to their limits as well. Light from TOT 618 has been stretched by cosmic expansion, shifted so far toward the red end of the spectrum that detecting it requires enormous telescopes and extraordinarily long exposures. Instruments must be cooled to near absolute zero, carefully calibrated, shielded from every possible source of interference. Computer algorithms work to separate genuine signals from background noise. Every single measurement carries multiple layers of uncertainty. Yet somehow, we can extract meaningful data from photons that began their journey 10 billion years ago. We can describe something unimaginably far away using numbers, equations, mathematical models. This achievement would have seemed like pure fantasy to earlier generations of scientists. It shows both how far human knowledge has advanced and how much farther there still is to go. The questions that emerge at this frontier extend well beyond black holes themselves. They reach into the fundamental nature of existence. What happened before the Big Bang, if anything happened at all? Why do the laws of physics take the particular forms they do? Is our universe unique, or part of some vast multiverse we can barely imagine? These questions remain highly speculative, but they grow naturally from the same curiosity that drives us to measure distant quasars in the first place. There's something profound about the simple act of seeing, of converting light into knowledge. When we observe something as remote as Tionane, we participate in a connection that spans nearly the entire history of the cosmos. An atom near that supermassive black hole emitted a photon billions of years ago. That particle of light traveled through space, through time, through the ongoing expansion of the universe itself, to end its journey in a human-built detector. This creates a direct physical link between the beginning of time and the present moment, between the impersonal laws of physics and the conscious awareness that can perceive them. To make such measurements is to bridge an almost incomprehensible gap, connecting our small corner of space and time with events that occurred when the universe was young. At the limits of human comprehension, science and wonder naturally converge. The deeper we look into the cosmos, the more we realize that the unknown isn't simply an absence of knowledge. It's actually the source of knowledge, the thing that makes curiosity possible in the first place. Without boundaries to understanding, there would be nothing left to explore. TON 618, enormous and utterly unreachable, embodies this principle perfectly. It stands as a constant reminder that there will always be more beyond our current horizon. More questions to ask, more mysteries to unravel, more to learn about the nature of reality. Perhaps that's the quiet truth underlying everything we discover about the universe. The edge of knowledge isn't really a line to be crossed once and for all. It's more like an endless landscape to be explored, where each discovery doesn't replace mystery with certainty, but reveals new layers of mystery beyond. The ancient light from TON 618 carries more than just information about a distant black hole. It reflects our own ongoing search for understanding, showing that knowledge can never be truly complete. Even in a universe that appears to be governed by consistent physical laws, there remains infinite room for curiosity. The human mind evolved to understand things at human scales, mountains and rivers, the curve of Earth's horizon. The reality near a supermassive black hole belongs to an entirely different order of existence. Yet, imagining what it might be like proves irresistible, because it allows us to test what we think we know about gravity, time, and motion. If you could somehow begin a journey toward TON 618, you wouldn't start in darkness. This object, like most active quasars, blazes with light visible across millions of light years. The accretion disk surrounding it spans a width greater than Neptune's entire orbit, outshining every star in its host galaxy combined. From a safe distance, it would appear almost star-like, except its brightness wouldn't flicker the way starlight does when viewed through an atmosphere. It would burn steady, pure, impossibly intense. As you approached, that brilliant point would gradually spread into a visible disk, a flat, swirling storm of superheated gas and plasma spinning at nearly the speed of light. The colors would shift with distance from the center. Far from the black hole, the light might glow with a soft blue hue. Closer in, it would shift through ultraviolet wavelengths, then into X-rays invisible to human eyes but deadly in their intensity. The energy in that inner region would be so extreme that matter no longer behaves as it does on Earth. Atoms would be stripped of their electrons completely, forming a plasma where charged particles spiral along magnetic field lines, releasing radiation as they accelerate. It's a realm of pure dynamics where motion itself becomes luminous, where the very act of falling generates light. The strangest thing about falling toward a black hole isn't what happens to you, it's what happens to time itself. From your perspective, the journey would feel perfectly normal, seconds ticking by at their usual pace. But to someone watching from a safe distance, your entire fall would slow to a crawl, then freeze completely at the event horizon. They'd see you suspended there forever, your image growing dimmer and redder until it fades into darkness. You, meanwhile, would continue falling, unaware that the outside universe is racing ahead without you. This isn't just a quirky side effect of extreme gravity. It's a fundamental truth about the nature of reality. Time isn't the universal constant we imagine it to be. It bends, stretches, and warps, just like space does. Near something as massive as TON 618, time becomes as malleable as clay in an artist's hands. As you approach that invisible boundary, the event horizon, the view around you would transform into something almost magical. Light from the accretion disk would curve and bend, forming a glowing halo that seems to wrap around the entire universe. Above you, all the stars and galaxies would appear to squeeze together into a bright, shrinking sphere. Below, the blackness would deepen into something beyond darkness, a void so complete it seems to pull at your very perception. Some photons near the horizon get trapped in circular orbits, racing around and around a black hole, before either escaping back to space or spiraling inward forever. You might see this trapped light as a shimmering ring, a brilliant border between the known universe and the unknowable interior. It's mesmerizing to think about, this cosmic lighthouse marking the edge of existence as we understand it. The moment you cross that threshold would be surprisingly ordinary. No flash of light, no sudden sensation, no dramatic change in the laws of physics. The event horizon isn't a physical wall or barrier. It's more like a point of no return in the flow of space-time itself. Think of it as the top of a waterfall in the fabric of reality. Once you go over the edge, there's only one direction left to travel. Here's where things get philosophically fascinating. Inside the event horizon, the usual relationship between space and time essentially flips. Outside a black hole, we move through space while time carries us forward. Inside, every possible direction through space points inward toward the center. Time becomes the dimension that determines how deep you fall. It's as if the universe has rearranged its most basic rules just for this one region of space-time. TON 618's enormous size actually works in your favor during this journey, at least initially. Smaller black holes would tear you apart instantly through a process scientists call spaghettification. The difference in gravitational pull between your head and feet would stretch you like taffy. But TON 618 is so vast, so massive, that its tidal forces near the horizon are surprisingly gentle. You could cross into the black hole completely intact, still conscious, still thinking, still experiencing the fall. The distortions would build gradually. As you descended deeper, light from the outside universe might still reach you for a while, but it would arrive blue-shifted and compressed, growing brighter and more energetic. The photons that followed you inward would carry the final messages from the universe you left behind, concentrated into an increasingly intense storm of radiation. Eventually, you'd reach a point where our best theories simply break down. Einstein's equations predict something called a singularity at the center, a point of infinite density, and zero volume, where the curvature of spacetime becomes infinite. But infinity in physics usually means we don't know what's really happening. It's mathematics admitting ignorance, a placeholder for phenomena beyond our current understanding. What actually exists at the heart of TON 618 remains one of the great mysteries of science. Some physicists think matter might be compressed into forms we can't yet describe. Others suggest spacetime itself might connect to another region, perhaps another universe entirely. There's even speculation that quantum effects could halt the collapse, creating something that persists in ways we can't imagine. The journey inward would end, not with an impact or collision, but with the complete breakdown of familiar concepts. Space would no longer be measurable, time would no longer flow in recognizable ways. There would be no before or after, no cause and effect, no clear distinction between observer and observed. Everything would converge into a state that defies ordinary language and thought. From the outside universe, this entire drama remains forever hidden. The effects of TON 618's interior can only be inferred through the gravity it exerts and the light it prevents from escaping. The inside of a black hole isn't really a place in the conventional sense. It's better understood as a region where our concepts of place and time stop making sense entirely. Some theoretical physicists propose that quantum gravity might replace the classical singularity with something finite and comprehensible. In this view, space-time itself could be made of discrete units rather than smooth, continuous fabric. Falling into a black hole might not mean disappearing into nothingness, but entering a domain governed by physical laws we haven't discovered yet. Then there's the puzzle of information. Quantum theory insists that information about physical systems cannot be destroyed. It can only be transformed or hidden. But if matter and energy vanish beyond the event horizon, what happens to all the information they carried? One intriguing possibility is that everything gets encoded on the horizon itself, like a two-dimensional hologram containing the complete history of everything that ever fell in. Another idea suggests information slowly leaks back out through Hawking radiation, preserving the universe's total information content over vast periods of time. If either theory is correct, TON 618 becomes more than just a gravitational monster. It becomes a library, storing unreadable data about everything it has ever consumed. This raises a profound question about the nature of existence itself. If your structure, your energy, your personal history gets preserved in some abstract form on the horizon, have you really been destroyed? The information would be scrambled beyond recognition, but not erased. The universe seems reluctant to forget anything completely. It transforms, conceals, rearranges, but it keeps its records. In this sense, falling into TON 618 might be less like disappearance and more like translation. Physical existence converted into pure geometry and information. Your story would continue, written in a language the rest of the universe cannot read, but preserved nonetheless in the fundamental structure of space-time itself. The event horizon represents something unique in science, a boundary not just of space, but of knowledge itself. Every observation, every theory, every equation reaches its limit at that invisible edge. Beyond it lies the realm of speculation, sometimes mathematical, sometimes philosophical, but always uncertain. This isn't a failure of science, it's a recognition of science's honest limits. The horizon embodies the unknown in its purest form, a reminder that mystery isn't the enemy of understanding, but its eternal companion. Yet, even at this edge of comprehension, reason and mathematics continue to function with remarkable precision. We can predict exactly how matter behaves as it approaches the horizon. We can describe the geometry of space-time with extraordinary accuracy right up to the moment our theories break down. The universe may contain mysteries beyond current understanding, but it also follows patterns we can trace to the very edge of the knowable. To imagine falling into TON 618 is really an act of intellectual courage, rather than morbid curiosity. It's the mental equivalent of crossing that boundary, exploring through thought and theory what lies beyond the reach of observation. Every scientist studying black holes is already falling inward in this metaphorical sense, descending deeper into layers of understanding. The equations describing black holes serve as maps of this conceptual descent, guiding thought toward questions where everything converges. What happens when matter, energy, space, and time reach their ultimate limits? The answer remains suspended, like the frozen image of a falling observer, existing as pure possibility. Perhaps that's what you discover on this impossible journey, that the final destination isn't destruction in any meaningful sense, but comprehension taken to its absolute limit. Beyond light, beyond time, beyond familiar forms of existence, there might remain something we can only call continuity. The persistence of existence in ways we can't yet describe or imagine. TON 618 stands as both a real astronomical object and a symbol of the horizons that define human knowledge. It's a place where matter, energy, and understanding all meet their boundaries, and beyond which lies whatever comes next, still waiting to be discovered. When light reaches its final destination and can no longer escape, something remarkable happens. The universe transforms from a realm of brightness and color into something governed purely by geometry and mathematical certainty. This isn't emptiness we're talking about, but a different kind of cosmic order entirely. The event horizon sounds like it should be a solid barrier, something you could touch or feel, but it's actually just a mathematical boundary, a point where space-time bends so severely that all paths lead in only one direction. There's no wall there, no surface, no material at all, just pure geometry, expressing itself through gravity's most extreme form. Here's where things get truly strange. If you watched something fall toward this boundary from a safe distance, you'd see it slow down dramatically as it approaches. The light from that falling object would stretch and redshift until it simply fades away. From your perspective, that object would appear frozen at the edge, suspended there forever by time's distortion. But from the falling object's point of view, nothing stops at all. It crosses the boundary smoothly, continuing its journey inward. Two completely different experiences of the same event, both equally true within their own reference frames. This shows us how relative our understanding of motion and stillness really is. Inside this boundary, the familiar rules still apply, but in ways that challenge our everyday thinking. Photons, those particles that carry all the light we see, can no longer travel outward. Their paths curve endlessly inward, trapped by the warped geometry of spacetime itself. Without light escaping, external observers have no way to directly see what's happening inside, yet we're not completely blind to this hidden realm. The mathematics of general relativity allows us to infer what must be occurring beyond that boundary. The equations tell us that spacetime continues to evolve inside, carrying matter and energy toward the center. But here's the fascinating part. The roles of space and time essentially flip. What we normally think of as forward, in time becomes inward toward the center. Every particle that crosses this threshold contributes to the black hole's total mass and energy. Nothing truly vanishes or gets destroyed. Instead, it becomes part of the geometric structure itself. The conservation laws that govern the rest of the universe continue to hold, even in this extreme environment. This changes how we think about absence and presence. The interior isn't empty nothingness. It's actually the densest concentration of something that physics allows. The silence there comes not from emptiness, but from complete saturation. Everything reaches its absolute limit, while still following the same fundamental principles that govern falling apples and orbiting planets. Even from outside this hidden realm, its influence extends far into space. It shapes the paths of nearby stars, guides the orbits of gas clouds, and somehow powers enormous jets that shoot outward at nearly the speed of light. These jets seem paradoxical, carrying energy away from a system that traps light itself. The secret lies in the spinning motion and magnetic fields just outside the boundary. As matter spirals inward, it twists these magnetic fields, channeling some energy into those spectacular outflows before the matter itself crosses the point of no return. The black hole's rotation drags spacetime around with it, creating a region where nothing can remain stationary relative to distant space. This phenomenon, called frame dragging, means that even light must rotate along with the black hole in this twisted region of spacetime. There's even a theoretical way to extract energy from this process, showing that the universe always leaves subtle openings for transformation, even in its most extreme states. The boundary between the visible and invisible represents more than just a physical limit. It's the line where predictability continues, but direct observation ends. We must rely on our faith in the consistency of natural laws to understand what lies beyond. In many ways, this mirrors humanity's long philosophical quest to find the limits of comprehension. Some theories suggest this hidden stillness might not last forever. Quantum effects at the boundary could cause slow evaporation through something called Hawking radiation. If true, even the most massive black holes would eventually fade away, particle by particle, over timescales longer than we can truly comprehend. For supermassive black holes, this process would take vastly longer than the current age of the universe. They might persist long after stars burn out and galaxies go dark, becoming some of the last luminous remnants in a dying cosmos. Silent monuments to an era when the universe was full of light and motion. In the deep future of the cosmos, when everything else has changed, these regions might serve as the final anchors of structure. They become keepers of mass, preserving the past within the curvature of spacetime itself. Their hidden interiors store everything that ever fell inward, maintaining it as part of the geometric framework of reality. The absence of light in these regions doesn't mean darkness in any familiar sense. It means the absence of observation itself. Yet this isn't something to fear, but rather a condition of perfect balance. It represents the endpoint of energy, the fulfillment of gravity's pull, the completion of every possible trajectory. The cosmos always tends toward equilibrium. Stars burn until they stabilize or collapse. Planets cool until they reach thermal balance. Even the universe's expansion moves toward uniformity. These extreme regions represent the ultimate expression of that tendency, places where balance becomes total and complete. Paradoxically, this invisible stillness remains incredibly active in shaping the visible universe. It organizes galaxies, influences the space between stars, and affects the path of light traveling anywhere near it. The hidden and the seen aren't opposites, but two aspects of the same reality, bound together by identical physical laws. When we think about it this way, the boundary between light and stillness becomes a connection rather than a division. The visible universe exists because of what happens beyond visibility. The blazing accretion disks and the quiet hidden cores aren't contradictions, they're expressions of one balanced system. Each new observation brings us closer to understanding how the universe maintains its harmony through these extreme conditions. The stillness beyond light will always remain unseen, but it continues holding the shape of the cosmos together, anchoring it with everything that has ever fallen inward. Perhaps in this quiet balance we find a reflection of something deeper about existence itself, even where perception ends. Even in the complete absence of light, the universe continues to be whole. That wholeness, unseen but complete, represents the profound stillness that lies beyond light's reach. Light has been traveling through space for over 10 billion years, carrying stories from when the universe was young and wild with energy. These ancient photons cross vast emptiness, moving through regions that might now hold new galaxies, or nothing at all. Some of this light reaches us today, some passes by unnoticed, some will never be caught by any instrument. The photons don't care about distance, they just keep moving, carrying quiet messages from what once was. We sit on this small world, orbiting an ordinary star, using delicate machines to listen to these messages. It's odd to think that light which left a distant object before Earth even existed can enter our atmosphere, hit a mirror, and end its ancient journey as a weak signal in our detectors. That signal gets turned into numbers, charts, and knowledge. The connection between something born near a massive black hole and our simple act of looking up spans distances almost too large for words to capture. This conversation happens every moment. The universe talks to itself through light, across every scale imaginable. When you glance at the night sky, it's easy to forget you're looking at history. Each point of light is a memory. Each dim glow represents an event that ended long ago. Stars are like letters written before we existed to read them. Galaxies form sentences in a story that unfolds across billions of years. These distant, brilliant objects wrote some of the earliest chapters, bright and intense and lasting. Their light comes to us as whispers, soft enough to be hidden by noise from our own planet, yet carrying more information than words ever could. We often think of the universe as distant, as separate from us somehow, but when we follow the path of that light carefully, the separation starts to disappear. The same physical laws that control black holes and their boundaries also shape the neurons firing in our brains. The same particles that once spun around those massive objects now drift through our blood. The atoms that make our world were created in stars that lived and died under identical cosmic rules. The universe isn't something we simply observe, it's something we belong to. Every observation is the universe examining itself. Every question continues its own development. On a clear night, far from city lights, you could look straight into the darkness and never see these distant objects with your naked eyes. They're too far away, too faint, their light stretched and weakened by time. But they're there, waiting in the depths. You could stare for hours and never glimpse them, but knowing they exist changes how the darkness feels. What seemed empty becomes full. Every patch of sky holds countless wonders. Every quiet moment carries echoes of creation. There's something calming about this idea, that the silence of space isn't the absence of sound, but the building up of it over time. The background radiation that fills the universe, the faint buzz of energy that telescopes detect, is the afterglow of everything that ever happened. It reminds us that nothing truly disappears, not stars, not galaxies, not even the light that leaves them. It all remains, stretched across time, growing dimmer, but not gone. The same applies to us. Our brief moments, though tiny on the cosmic scale, become part of that continuity, absorbed into the same vast persistence. Scientists studying these objects often focus on numbers. Billions of solar masses, billions of light years of distance, brightness beyond measure. Those numbers are impressive, but they're not the complete picture. Behind them lies something quieter. The simple fact that we can know any of this at all. Human beings, confined to one small planet, can understand the physics of objects so far away that their light started traveling before our species existed. This ability to reach outward with thought, to find patterns in what seems infinite, might be the most remarkable thing the universe has accomplished so far. The act of understanding feels like an echo of cosmic creation. The same forces that formed black holes and galaxies also made minds capable of seeing them. Curiosity isn't separate from the universe, it's one of its natural results. The same laws that make matter collapse under gravity also make consciousness reach outward, toward discovery, toward meaning. Gravity draws everything inward, but it also draws thought outward. These distant, unknowable objects are part of that conversation. Their existence invites questions, and the questions complete the circle. If you sit quietly, perhaps in the deep hours of night, and think about this, the distance starts to feel smaller. You and that distant black hole seem less like separate things and more like parts of one process. Energy becomes structure. Structure becomes awareness. Awareness returns to energy through observation. Everything connects, not through poetry, but through physics. It's the same universe, continuous, from the core of distant black holes to the quiet breath you're taking right now. The space between us and that ancient light isn't empty. It's filled with time, with the slow unfolding of everything that ever was. Light from these distant objects moves through that space, and so does light from our own sun. The signals from our satellites, the faint traces of every radio transmission humanity has ever made, all travel outward together, mixing into the same fabric. Somewhere far in the future, a fraction of that signal might drift through another galaxy, long after we're gone. Someone or something might notice it the same way we notice these distant lights. The exchange never ends. Think about it long enough, and the universe starts to feel less like a stage and more like a conversation. Each particle, each photon, each gravitational wave is a line of dialogue. Black holes speak in bent space-time, stars speak in radiation, planets speak in motion. Somewhere in that ongoing exchange, life began to listen. Every observation, every experiment, every quiet night of looking up is part of that same act of listening. One that began billions of years before there were eyes to see or minds to wonder. The night sky above us is the most ancient text we have, written not in symbols, but in light. Each photon is a syllable, each spectrum a word, each galaxy a chapter. These distant objects represent some of the oldest pages in that text, preserved against the erasing effects of time by distance and gravity. We've only begun to learn how to read it. The more we learn, the more we realize how vast the story is, and how small our role, yet how essential. Without readers, even the greatest story remains unread. Without curiosity, even the brightest light remains unseen. It's remarkable how looking outward changes what we see inwardly. Knowing that black holes exist, that gravity can shape time and light so completely, changes how we think about our own existence. It puts our lives in perspective, not to make them smaller, but to expand them, The same physics that bends starlight also shapes the rhythm of every heartbeat. The same entropy that drives galaxies toward balance governs the fading of a sunset. The patterns repeat, from the cosmic to the intimate, endlessly. There's comfort in that repetition. It means the universe is consistent, reliable, complete. It means that light from the most distant objects, though far away, follows the same rules as the light in your room. It means that even at the edge of understanding, we remain within the same structure. Every observation brings the infinite closer, not because the distance changes, but because our understanding bridges it. Imagine you could see the sky, not just as points of light, but as it truly is, a map of time. Closer stars would shimmer with recent light, while distant galaxies would appear as faint memories, their glow softened by age. The most distant visible objects would be among the oldest lights we can see, remnants of the universe's youth. Looking at such a sight would be like looking through layers of history, all compressed into one field of vision. Every direction would point to another era, another chapter of creation, another piece of the same story. At the center of that field, unseen but certain, would be the awareness looking back. That awareness is as much a part of the universe as any star. We tend to separate ourselves from what we observe, but there's no real boundary. The atoms in our bodies are ancient, recycled, countless times, through stars and cosmic dust. Some may have come from objects like these distant giants, forged in the same furnaces of gravity and light. When you consider it this way, the distance between observer and observed becomes smaller still. The light we study once flowed through matter that may now flow through us. The cycle is complete, continuous, endless. As the universe expands, most of its light will eventually drift beyond reach. The most distant galaxies will fade from view, their photons stretched into wavelengths too long to detect. Massive black holes will remain, slowly consuming what's left of their surroundings until even they cool and quiet into invisibility. The cosmos will grow dark, and the last echoes of creation will fade into background radiation. But the fact that we can see any of this now, here in this brief window of cosmic time, is extraordinary. We exist during the era when the universe is visible, when the light of its beginnings still reaches us. We are witnesses to its story, while it's still being told. Though that story will continue long after we're gone, our awareness of it gives it meaning in this moment. The light from distant objects will keep traveling whether we watch it or not, but knowing it's there changes everything. It turns the night sky from emptiness into connection. It transforms silence into conversation. It gives weight to wonder. Here we are, you, me, and the infinite night. The same night that has covered every world since the beginning. The same darkness filled with ancient light. Somewhere out there, these distant objects still shine, unseen but not forgotten. Their photons still cross the distance toward whoever might come after us. Somewhere here, in this small corner of the same universe, we keep looking up, still listening, still learning, still part of the same unfolding story. There's no need to end that story because it never really ends. The light keeps traveling, the questions keep forming, the stillness beyond light keeps holding everything together. The act of wondering, quiet, steady, endless, keeps it all alive.